Satellite meeting. It's a pleasure to have you all here. It's also a pleasure to have all the speakers of this session. The first speaker is going to be Gustavo Martini Dapian from Universidade Federal do ABC. He's going to be talking about tuning spin splittings in 2D compounds. And I'll pass on to the speaker. He has 26 minutes plus time for questions. And so here we go. Oh, 24, sorry.
24? Okay. So total is 30, Alexandre, 36? 30? Okay. So good afternoon, good morning, everyone. Or good night sometimes. So I would like to thank Alexandre and Nathan for inviting me to talk at this very nice meeting. It's very important to put this community together here to discuss physics. So I'm very glad to be here at the IFT again. Okay. So I'm going to talk about tuning spin splittings in 2D compounds. This is related to some works we've been developing in our group at UFABC, even though I will be moving in a couple of months to the Physics Institute at the University of São Paulo. And I'll be moving together with, oops. Okay, I'll be moving together with my group. This is the Computational Materials Science group at the UFABC. Before I talk about my work, actually, I would like just to comment briefly on what we do at UFABC. So we have some works that are focusing on materials informatics. We just had an INCT, that is an National Institute for Science and Technology, funded by CNPq. So this INCT is on materials informatics. So this is a big project putting together around 30 researchers from Brazil, and we'll be studying this kind of research. The idea is to put together material science with data science tools, including machine learning and so on. So I'll be talking a little bit about this during this talk. We have another branch that studies quantum materials. This talk today is also going to be somehow related to these quantum materials. And another area of research focuses on energy materials that includes a very strong tendency for halide perovskites that are new materials that have been applied in solar cells recently. We have collaboration with experimental groups and some friends from the US as well working on this. Well, let me go back to my talk, tuning spin splittings in 2D compounds. The idea of this talk is to try to propose a way to engineer the properties of materials or engineer materials with targeted properties. We define a property and then we try to find what are the materials that optimize this kind of property. So we are interested in spin splittings, and this is somehow related to spintronics. Spintronics, the overall idea of spintronics is to develop devices that work, instead of working with electron degrees of freedom, or it has a current or doesn't have a current, the idea is to work with spin degrees of freedom. So you would have a current of spin up electrons or current of spin down electrons, and by tuning spin up and spin down, you could transport information through these devices. So this is a very broad area of research, okay, spintronics. But I like to say that, okay, this is an application of our studies, but as we do basic science, I like to say that we like to understand the fundamental properties of materials, so this is already a good enough motivation for our work. We would like to understand better how this kind of spin splittings occur in materials, okay? So I would like to put two main ingredients for this talk today. The first ingredient is band dispersions and spin splittings, okay? Whenever you have a semiconductor, owing to some symmetry constraints of these semiconductors, that is either time reversal symmetry or inversion symmetry, usually you have, in standard semiconductors, you have that the spin up and spin down bands are degenerated. So here you have a reciprocal space. This is the band dispersion. And you see that both spin up that are blue and spin downs that are red, they are degenerated. Sometimes you have some materials where you break this, one of these symmetries, either time reversal symmetry or the inversion symmetry. And whenever you break this symmetry breaking can lead to some spin splitting in the materials that you are dealing with. So if you break time reversal symmetry, for instance, applying a magnetic field, you will have the Zeeman effect. So you see it here that the spin up band is not degenerate with the spin down band anymore. Or if you break inversion symmetry, you can have a different kind of spin splitting that is called the Rashba spin splitting. And spin up and spin down bands are not degenerated anymore. So we would like to understand this kind of spin splittings in two-dimensional compounds. So this is about spin splitting in materials generally. So the other ingredient that I want to put in this work or in this talk is related to materials databases. Okay. So we've seen this area of materials informatics has been growing lately, and we've seen the rise of many repositories of materials in the community or in the literature. Okay, so this is a paper published some years ago that talk about materials databases, and this is important because this is going to be the main tool we aim to use in our work. Okay. So, for instance, this is one database in ICSD, Inorganic Crystal Structure Database. The general idea of this database is the following. So whenever you grow a new material, you characterize it using X-ray diffraction. So when you characterize it using X-ray diffraction, you get the structural properties of this material, lattice parameters, the position of each atom inside this, the unit cell. Okay, and experimentalists, every time they characterize a material, they used to put this information into this database that is ICSD. Okay, then a few years later, in this materials project, what these guys did, these guys they are researchers from Berkeley and MIT, and so they worked with some scripts. And they use quantum mechanical methods based on density functional theory that basically the idea we solve the Schrödinger equation for a material. And they simulated all the materials that exist. So if you enter in this database, materials project, you are going to find all simulations of all materials that exist. And you can find in these databases all the properties of these materials. This is a very powerful tool. Okay, and we aim to use this kind of tool to find the materials that fit better for a specific property. Okay, well, I don't have much time, so I'm going to skip the other repositories, but there are many. Oops, I think everything is okay. No, I think it's okay. Okay, we can look afterwards. Okay. 1 minute more, Alexandre. Okay. Okay, many different databases, and some of these bases are specific for some specific properties. Okay, so this is the second ingredient of our talk. The idea here is that we want to accelerate the way we develop materials or that we discover materials. So we want to change from the conventional approach to develop new materials, and we want to go to a new way of developing materials that we call inverse design way of developing materials. So the standard way is the following. Some people go to the lab and they mix elements together and build and grow a new material. Okay, then they characterize this material using many different techniques and look for the properties of this material. Once they have the properties, they try to find a good application for this material, and that's how things work. This is more or less you trial and error option. Okay, so what we want to do is the opposite. we want to start from the property that we want, okay? We start from the desired properties, and then we search in these databases for the materials that fit better for this specific property, okay? So this should be much cheaper and faster than the traditional method of designing materials, okay? So for 2D materials, we already have many 2D materials that have been characterized experimentally, grown experimentally, okay? And there are papers discussing about this. I would say that there are a little bit more than 100 different materials, 2D materials that are stable and that have been characterized. But it would be important to expand the number of these materials, of these 2D materials, in order for us to expand the possible applications of these materials. And that's what we want to do, okay? So what we did, we built a database of 2D materials where we calculate all 2D materials that exist, and we calculated this property that I've talked to you about, the spin splitting of all 2D materials. So this has been published in this paper. The journal is called Scientific Data. Maybe you haven't heard about it. It's kind of a different journal, and it's interesting because when you read the scope of the journal, they say, oh, you don't even need to have new science to publish it in this journal. It's enough to have data, to post the data. But in our paper, I like to say that we have data, a lot of data, by the way, but we have new science. We give some hints about new physics, and so we put everything together in this paper. So what we did, we go back to these band dispersions, these different types of spin splittings into the compounds. You see that you can have many different types of spin splittings. So you have the Zeeman spin splitting, you have the Rashba spin splitting, and you know, this is actually not new. So people have been discussing this kind of spin splitting since 1955, so this is more than almost 60 years ago, okay? So this is Jean Dresselhaus, that was the first to discuss spin orbit effects in zinc blende semiconductors. So you see here that these bands are spin split, owing to the presence of spin orbit coupling. So what we need to do, or what we did to build our database of spin splitting, we wanted, besides simulating all materials, okay, and getting all the spin splittings, we wanted to classify these different types of spin splittings in each different type of spin splitting that we might have. So here you have the Rashba spin splitting that I have mentioned before, Dresselhaus spin splitting, Zeeman spin splitting. And you know, this, my students, they didn't want to show this because they didn't know how to explain this high order. So we called high order because we don't know exactly how to explain this kind of spin splitting, but I'm going to explain to you what happens, but they are not characterized as any other one of these types. So in order to characterize whether a spin splitting in a band structure is one or other, we have to look for some physical properties that here we call design principles, okay? So there are some design principles that are physical properties that are mandatory, the materials to have, in order to show this kind of spin splitting. So the first that we call enabling design principles, they are common to all types of spin splittings. You must have, the atoms that compose this material, they must have a large spin orbit coupling, usually heavy atoms, okay? And besides that, you must have non-central symmetric structure. Then afterwards, the other that we call unique design principles because they are unique for each type of spin splitting. And depending on whether you have electric dipole, the symmetry of the K point that where the spin splitting occurs, okay, whether it's a time reversal invariant K point or not. And this is very technical, but it's how you model the Hamiltonian that you are using to simulate this type of spin splitting. Depending on each of these tasks, you can classify the splitting as Rashba, Dresselhaus, Zeeman, or high order, okay? So this is discussed in this paper, okay? And so that's what we did. What we did is to calculate the spin splitting in all 2D materials available in a database. So we go to this online database that is called C2DB. Okay, it has 3,800 ab initio calculations for different 2D materials. And then we start filtering. First, we want semiconducting materials. Then we end up a little bit more than 1,000 compounds. Then we want materials that have non-centrosymmetric structure, around 500, non-magnetic order, 400, and so on. So we end up with 436 materials, and we performed ab initio calculations with spin-orbit coupling on the full band structure for each of these compounds. Okay? And then we run our script that I'm going to show in a while for you, and we try to running this code, we can classify each of these materials and each of these spin splittings as either Rashba, Dressel, Zeeman, or high order. You see that this number is larger than this number. That's because you can have the valence band and conduction band spin splittings, and at different K points, high symmetry K points, you can have different types of spin splittings. Okay? So all this algorithm that you use to calculate or to evaluate all these symmetries, it's available in at GitHub. And this is the script that we run. Basically, we go through the full band structure of our material. We check the symmetry of the K point. If it's a time reversal invariant, then we go this way. If it's not a time reversal invariant K point, you might have Zeeman spin splitting. If not, we look for the band's dispersion. This is the difference between high order and not high order. So if the band dispersion is like this, it goes up here and goes down here, this linear in K spin splitting, then it can be either Rashba or Dressel, depending on whether it's polar or not non-polar. And sometimes we see dispersions that are like this. Both bands go down, and then we classify these guys as high order spin splitting compounds. Okay. Okay. So we put all this information in these tables. You see for each of the type of spin splittings, for each of the K point, we calculate the spin splitting, and all the other properties, whether it's valence or conduction band, and this has been made available, fully available in Materials Cloud. These are some examples of spin splittings for different compounds, either Rashba spin splitting here, what else? Zeeman spin splitting, so we can find many, many materials with large spin splittings. All this material is available, fully available, so this was a lot of work, actually. So all the ab initio calculations that were performed with VASP, they are available in this Nomad repository, all the inputs and outputs for each of the more than 400 calculations. We have all the band structures calculated with spin projection. We have the tables that anyone can read, and we also have the database files that you can use some automated way of retrieving data as either JSON or MongoDB. Okay. Okay. So now that we have a lot of data, okay, what can we do with this data? It's easy to generate a lot of data, but then what do you do with a lot of data? So that's the question everyone that is looking for this data science tools should look for. So, okay. So the question that we would like to answer is, okay, what is the best material? So for a specific properties, sorry. Can we use the data to propose new materials? Okay, so these are the questions that we would like to look for. I'm going to show some information about, I have information about Zeeman spin splitting, Rashba spin splitting, and band gap. Okay, and then the idea is that we aim to use Bayesian statistics or Bayes' theorem to try to look for the probability of a material to have a large, for instance, if the question is, what are the materials that lead what are the conditions that lead to a very large Zeeman spin splitting, for instance. And what is the crystal structure that leads to a large Zeeman spin splitting? Or what are the atoms that lead to a large Zeeman spin splitting? So that's what we would like to do, and we use Bayes' theorem in order to update the probability of having a large spin splitting as you give more information, okay? So what is the information that you have before? Oh, the material has a large Zeeman spin splitting. What is the further information that I'm going to give my material? The crystal structure, for instance. So large spin splitting and this crystal structure. What is the probability of having a large Zeeman spin splitting? This Zeeman spin splitting and having these atoms belonging to the crystal. So what is the probability, the updated probability of having a large Zeeman spin splitting? And then we see and we can track the crystal structures and the atoms that maximize that property, okay? So in order for us to do that, we have to tell the computers how to deal. I'll go very quick through this technical stuff, but in order for you to simulate this updated probability, you have to tell the computer what are the materials that you are dealing with. So we have to take each element, each compound, okay, molybdenum disulfide, for instance, and we transform molybdenum disulfide into a huge vector, okay, where it has around, I think there are more or less 70 different types of atoms that can be anions and cations, and then we have this 70 times 2, so this is a vector with a dimension 140. And we use Boolean variables, so if it has molybdenum, then at the position of lithium, it's false, 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 and when molybdenum comes, it's true, okay? Then it's false, 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 antimony is true again, okay? So we use this to tell the computer what are the atoms that belong to the material we're looking for. We also have to tell what is the crystal structure of the material, so this is more challenging. Telling the computer what is the crystal structure is much more challenging. And so we use some fingerprints. There is this reference. We transform this crystal structure into a vector as well, okay? So each material has a different vector, and then we map this high dimension vector into 2 dimensions, and you see that different materials becomes clusterized. And then we put, the idea is that these different clusters, all materials in these different clusters, they have similar crystal structures. So we have 25 different clusters, and we use this as the information for crystal structure, okay? Well, just analyzing the data very briefly here, we can look for Rashba spin splitting, and so this is the distribution. You see that most materials have Rashba parameter smaller than 2 eV angstrom, okay? The same for Zeeman spin splitting. You see most materials have Zeeman spin splitter smaller than 0.1 eV. So this is a fingerprint of Zeeman spin split. Band gap, you see that most materials have band gaps that are smaller than 2 eV. So how many minutes do I have? 2? Okay. Okay, so I'll skip this. I had some examples for Rashba, Rashba parameter, but this is, I'll focus on Zeeman spin splitting, okay? So what we do is the following. We want to have materials with a Zeeman spin splitting larger than 0.1 eV. What is the probability within our database of having such a spin splitting? And I tell you, the probability that we call prior probability is 0.22 or 22%, okay? So, and then we use Bayes' theorem to update this probability, and I tell you, okay, from 0.22, what if your crystal has this ABCC4? This is some crystal structure for 2D materials. What if the crystal has this structure, what is the probability? Then the probability of having a Zeeman spin splitting larger than 0.1 increases to 59%. This other guy, 53, and so on. And this crystal structure here, the probability of having a large spin splitting is 0.01. So you see that we calculate, we look what are the crystal structures that maximize Zeeman spin splitting. The same for atoms. So let's look for bismuth, for instance. The probability of having a large spin splitting increases to 51%. So bismuth, looks like bismuth maximized this spin splitting. Then we put together, okay, these are just the crystal structure. We put together the cations that maximize the Zeeman spin splitting. We put together the anions and the crystal structures that maximize our target property. So we take this and we mix everything together, okay? And we look for new materials now that were not in our initial database. And then once we calculate these new materials, we had, I think, 14 new materials that were not in the initial database. And we simulate them. These are new compounds. All of them have Rashba spin splitting that is larger than our target value, that is 0.1 eV, okay? And some of them are even semiconductors, as this one. So you see, this iridium, tellurium, iodine is one example of a material that has large Zeeman spin splitting, and as we wanted, okay? So, well, I'm coming to an end, Alexandre, and so the main messages that I would like to pass to you are the following. This inverse design way of looking for materials is a powerful tool to find materials with optimized property. I gave you an example of Zeeman spin splitting, but this is just an example, and similar things can be done to any other property that of interest, okay? And we've built this database. It's fully available in this website, and it's freely available as well, okay? Okay, Alexandre, that's it for now. Thank you to all, okay?
Okay, so the session is open for questions. Just to remind those who are watching online that you can submit your questions on the system, and I'll read them to the speakers. Do we have questions? Eric?
Sorry, just one question about terminology. When you say you have broken time reversal symmetry, I was confused because I thought you would need a magnetic field. So so you're telling me your spins are polarized in this system, and which are the spin texture in this high order guy? So I was curious about that.
Okay. So the example here, the idea here was just to give an example of how, so we don't apply a magnetic field and we eliminate all magnetic materials, because whenever you have a transition metal, you already break this time reversal symmetry. So this is something induced just by the spin orbit coupling that would break this time reversal symmetry, okay? And for the other question, what was it? So yeah, it can vary a lot. So when you look for spin textures in these compounds, depending on the material that you look, and at the K point that you look for spin texture, it can vary a lot. So we studied it, not maybe we have not devoted enough time for this, but we couldn't find any specific descriptor for characterizing the spin texture in these compounds, at least for those which we have looked for.
Okay, last question, because we have to move on.
Is about the last materials that you showed, about the materials you obtained after all this analysis, and you obtained the band structure, isn't it? Did you relax the material that you found the stability of these materials that you obtained during this process?
This is a very good question, actually. Here. Yes, we optimized it. We minimized the forces in the material. So, and relax the lattice parameters and the internal position of each atom. But we have not calculated the convex hull, for instance, and not looked for the dynamic stability of this material. So this is important. The idea here was just to show the tool and to propose the tool how to work with this. Even iridium is very expensive, so I've shown this to an experimentalist and he said, okay, try something different than iridium and we might try to synthesize. But yes, this has to be done in order to see if it would work really. Okay.
Okay, so let's move on.
Tá certo assim? Ok, beleza. Isso, deixa eu só fazer um negocinho. Antes de você fazer, deixa eu só pegar aqui no slide. Eu tenho que liberar. Tem que liberar aqui ação de slide. Isso, 18. Não ocultar. Ok, daí vamos voltar lá. And we go. Ok. Está apresentando, né? Okay, all right.
Okay, so the next speaker is Luis Gregorio Dias, and he's going to be talking about emergent parafermionic zero modes in fermionic systems.
Okay, first of all, I'd like to thank the organizers for putting together this very interesting session. I didn't have the opportunity to go to the March meeting this year, but it's good to participate anyway in this satellite session here. So today I'm going to change gears a little bit from what Gustavo just told us, and I'll tell some story about these parafermionic zero modes out of fermionic systems. So the idea here, and I think I need to click somewhere to get the pointer moving. There. So the starting point here, and I hope this will serve Eric in the next talk as well, is the story of the Majorana zero modes that some of you might have heard and has been in the literature for at least the last 10 years. And here's a very brief primer about these Majorana zero modes. So we all know fermionic operators, how they work, like electrons without spin. And so if you can create a fermion out of vacuum and you get a particle, let's say, and you can destroy this particle and get back the vacuum, and then you have the antiparticle. And these particles or fermions, they obey these very well-known properties. For instance, if you square this operator and apply to any of these two states, you get 0, the other one, 2, the same thing. And of course, if you switch two fermions, you get a -1. We have, not only you can count the fermions that you have in the system, you can have either 0 or 1, so you have this number operator, but also you can define a parity, right? So if you have 0 or a system of many electrons, you have these well-defined parity operators that we can essentially define as -1 to the power of n, where n is the number of particles. Now, this is a representation that we know how to use, but there's an equivalent representation that in terms of operators that are their own antiparticle, if you wish, or if you dagger them, you get the same thing. So these are usually called Majorana operators, and they have similar but not identical properties as the regular fermions. In particular, if you square a Majorana operator, you get 1 and not 0. Now, this is essentially a change of basis, if you wish. So you can write regular fermions in terms of 2 pairs or 2 Majorana operators if you want, and you get the same properties that you had here. And you also can write it the other way around and write a single Majorana operators in terms of a creation operator for a fermion and a destruction operator for the same fermion. And you get a mixture of these two. So if you have, say, the particle and the antiparticle, or the filled glass and the empty glass, your Majorana is a half-empty glass, right? And then if you dagger it, you get the same thing. Now, the search for these particles or quasi-particles in condensed matter which have these properties has been going on for, say, the best part of the last 10 years, and with mixed results. And the key model that we are looking to realize in nature or in devices is the so-called Kitaev model for a P-wave superconductor in 1D. So the idea goes that if you have a system of spinless fermions that have, say, a tight binding term plus a superconducting pairing that connects fermions in different sites, so it creates what we call P-wave superconducting pairing. You can rewrite these operators here in terms of Majoranas, and you get a chain of Majorana operators now. And one of the regimes of this chain is you have isolated Majorana modes at the end of the chain, and that's essentially illustrated here in this cartoon. So this is the so-called gap topological regime, where you have these Majorana quasi-particles at the ends of this chain, and the whole idea is to try to figure out an experiment that not only realizes this model, but also can detect these Majorana modes at the ends. Now, this is, of course, not easy, but let me tell you that how can you try to look for models that can be realized like that. So let's say of course, you want this topological regime, or you have these Majorana zero modes isolated. Now you can say, okay, let me reverse engineering this Kitaev model, and I will start with a chain of Majoranas. And I know that this chain of Majoranas, I can, by hand, disconnect the last 2 modes. And I'll reverse engineering it, so I'll rewrite these Majorana operators in terms of fermions. And then I see what kind of fermionic mode or model I get, right? That I could perhaps try to realize in the lab. So this is also one way to get back this 1D P-wave superconductor, and is a very natural way to show that the Kitaev model actually works and gives us what we want. Now, of course, to realize this model is not easy, but let's see if we want to go one step further and go beyond these Majorana modes. And I'll tell you the reason why it would be interesting in doing that in a little bit. But let's talk to their older cousins, or their ZN cousins, which is the theme of my talk, which are the so-called parafermions. Now, imagine that instead of a fermion, which has 0 and 1, a Fock state of Fock space of 0 and 1, you would have some sort of other particle that you have a Fock state of 4 states. Like, you apply an operator to the vacuum, you get 1, and you apply the same operator to this one, and you get 2, and then you apply this to 2, get 3, and only when you try to apply to 3, you get 0, right? So you don't get 0 here, you get 0 after applying it 3 times. So this is a scheme, and these operators actually can be thought in terms of the algebra that they obey. They're called Fock parafermions, and they were introduced in 2014. Now, we can try to play the same game here that we did with regular fermions with these guys. And of course, now you also have a number operator, and you have a parity operator, but this parity operator, instead of having only 2 values, can have 4, right? You can have +1, +i, -1, -i. So that reflects this Z4 symmetry underlying the algebra of these Fock parafermions. Now, with that, we can try to get the Majorana, the Z4 Majorana operators. Here we're calling Z4 parafermions. And they would have the property that if you take a parafermion operator to the 3rd power, it will be equal to Dagger. Instead of just Dagger equals itself, you would have to take it to the 3rd power. What's the advantage here? Is that these operators, they don't have like fermionic exchange symmetries or exchange statistics, but they will have an anionic statistic right off the bat from just these definitions here. So that's something that might be useful, and we'll try to keep that in mind on the way forward. But let me tell you that since 4 is a double of 2, there's a hidden Majorana in there, so that the description in terms of just Majorana or purely fermionic operators might not be so hard because of this property that if you take chi-square and you take chi-square Dagger, because of these properties, you get the same thing. All right. Now the question is, can you get a θF chain of these types of Majorana cousins or these Z4 parafermions? And the trick here is try to get that reverse engineering that I was telling you about. So you construct a chain of these zero mode or these parafermion, these Z4 parafermions, and you just let 2 of them hanging at the end, and you write this model in terms of these parafermion operators, right? So I did this by hand. Notice that the chain here starts at j equals 1, so this chi 1 is not present here, and this psi n is not present here as well. So the 2 end modes, and these are the 2 types of parafermions that I'm defining here. Like in Majorana, I can define 2 types of these guys, and they are just left there. They're 0 modes. So if we reverse engineer this mode and try to write this in terms of fermions, it can be done, and that's my student Rafael who did all the work, and you can quickly realize that it's a lot of algebra, but you can have a representation of those Fock parafermions that I told you about in terms of regular fermions, but now they need to be spinful. So, okay, you go through all the algebra and you rewrite, reverse engineering the model, and what you get a mess. So you have an electronic model now that has all the properties that you want, but has very weird terms. For instance, at the very beginning, you have a tight binding model of spinful fermions with a p-wave pairing. Okay, we can live with that, but it's a spinful p-wave pairing. Not only you have to pair electrons on different sites, but they have to have opposite spins. All right, so let's try to engineer that. But now your model becomes strongly correlated. Means that you have 2-body interactions with some weird structure. So you have both 2-body operators, some 2-body p-wave pairing as well, and then you have some sort of spin orbit terms that now involve 3 bodies. So now we're going into the realm that is not really condensed matter. It looks more like quantum chromodynamics or something. Okay, but that's what the algebra gives us. So let's see what you can do with this model. And of course, you have also some sort of p-wave pairing, like a 3-body term. So the question is, yes, we can realize this model in terms of purely fermionic operators, but then things get complicated, and then we not only would have to propose mechanisms to get all these terms realistically in materials, but also we'd like to have a way to see first what's the phase diagrams, where do I find the phases I want, but also how to detect them. So the phases, we can look at the parameters of the model and say, if I take these interacting terms to 0 and the pairing to 0, I just have a trivial metal, just a tight binding one-dimensional system. Now, if I take the interactions to 0, I get 2 copies of the Kitaev model. So we have like a 2 times Z2 Majorana kind of model. So this is a gap system with 2 Majorana 0 modes. And now if I take everything equal to delta equals W equals T, then I get my gap system with parafermionic 0 modes, and I can summarize all that in this phase diagram. And I like to reproduce this phase diagram with some kind of detector. And I like this detector to be something that I can realize in the lab, like, for instance, a quantum dot. So again, in this corner, I have the trivial metal. In this corner is the gold, where I have these Z4 parafermionic edge states. And here I have just 2 copies of the Majorana modes. So I'm going to go a little bit faster here, just to show as a proof of principle that if you have your Kitaev chain for Z4 parafermions and you attach a quantum dot to that, where you can measure, say, the charge or the occupation of the dot, or even the local density of states in this dot, these measurements could give you some hint of that phase diagram I was telling you about. So here is how we calculate. We use this matrix randomization group to do these calculations. And we are all also interested not only in the charge, but also in the local density of states at 0 energy that we can, in principle, measure in a transport experiment through this dot. And if I just measure this quantity, I already have a signature of those 3 phases I was telling you about. So a trivial phase, which is this black line, which shows nothing in the quantum dot. I have the Z4 phase, which is the blue line here, which I show these 2 peaks at depending on the dot energy. But also I have something showing here in red, which is this other 2 times Z2 phase, which is also in this regime, and the one that has 2 Majorana modes. So I'd like to differentiate between the blue and the red. Then it is a little bit more tricky, that I have to look at the very fine details around these points. For instance, if I subtract this data point here from the data, I now could, in principle, see a difference between this phase and this phase. And in a quantum dot, you can also measure the charge. And if I would try to measure the charge in one of these points, I would get an overall curve that looks more or less the same. But if I differentiate this curve regarding to say, the trivial case where I can always realize or calibrate with another system that is non-topological, I could get some signature of the charge that could be measured for the Z4 phase. Now, how much time do I have? Like 5 minutes, okay, all right. So in the last 5 minutes, I want to tell you about another system that is not as easy to simulate or to get parafermions out of an all-electron system, which is Z3 parafermions. So what is Z3 parafermions? We play the same trick as before. We have to construct some sort of weird Hilbert or Fock space of 3 states, 0, 1, and 2. And an operator that applies on 0 gives you 1. The same operator applies on 1 gives you 2. And you try to apply this operator on 2, it gives you 0. Okay, so these now have not only the number operator, 0, 1, and 2, but also a Perry operator that has this triangle shape form. So it's 1 e to the 2 pi I over 3, e to the 4 I pi I over 3, and it will go back to 1. So from here, you see that there's no -1 here. So this is a crucial thing that is missing, and is something that gave us a lot of trouble in order to get a model, an electronic model. And another interesting thing here is that there's no hidden Majoranas. There's no, you can construct these Z3 parafermion operators here, but you cannot get a situation where you square one of them and you get to the dagger of the same square operator. They have these properties that you have to square the operator, it goes back to the dagger of that same operator, right? And the anyonic statistics is even weirder. I mean, if you exchange two of these parafermion modes, you get e to the 2 pi I over 3 and not I or minus 1 as we had before. Okay, but why would we care about these Z3 operators? Well, it turns out that if you want to build a universal quantum computer out of topological quasi-particles, such as Majoranas, you cannot do with Majoranas or Z4 because they're or even with Z3 because they're so-called Eisen operators, and you cannot construct all the gates that you need for universal quantum computation with these guys. But you have many Z3 parafermions. You can produce what is called Fibonacci anyons, and with these Fibonacci anyons, in principle, you could have a universal topological quantum computation, which would be the dream for those working in the field here. So Z3 have this, interesting prospect, and the question that we ask ourselves is, okay, can we get Z3 parafermionic modes at the ends of a 1D model out of electrons, right? And it turns out that you can play the tricks that we did before. You can in principle, define an operator like this Z3 Fock parafermion in terms of electronic systems, and it has all the same properties. But here, you have to try to forget the double occupancy state because it cannot go into our Fock space here. So, okay, say you have very strong electron-electron interactions, and this guy is at very high energies, and okay, I can maybe put this under the rug, and you have the right algebra, and then you do that reverse engineering of the Kitaev model with the two hanging parafermionic modes at the end, and you write them in terms of fermions. And you get now a very weird model. First, you would have those P-wave superconducting terms that, okay, we can live with that. You have strongly correlated properties. You have two-body interactions. I can also live with that. But now you get this term that not only is non-local, you have these strings attached to it. I mean, say the operator at site J depends on the history of all the sites before J, and it doesn't preserve parity. Okay, and now have an electronic system that does not preserve parity, and that's a big problem. Okay, so Rafael actually worked out these calculations, and he discovered that this thing can be thought as a result of a sort of a mean field approach or mean field operation that you do in a more general model that would have all the same interactions as before, but you have these terms that have three-body interactions that does preserve parity, but is much harder to deal with. But in principle, this model here is related to the other one via transformation that puts them in the same topological sector, if you want. So if you look at both the entanglement entropy and the energy gap of the low-lying states of both models, you see that both of them would have a transition to a phase where you would have, say, these topological edge modes at the end of the chain. And in this case, you would have a actual topological phase transition, and the other one would always be topological. And most importantly, you can show that you can go from one model to the other by changing one parameter and never closing the gap. That's one of the hallmarks, that they are both in the same topological phase. and both of them display these edge modes, and we can actually calculate the edge modes for the two models and compare with the exact results that you would get from the exact parafermionic chain, and everything seems to be working. All right, so the thing here is that you have a parity preserving model that is made out of fermions that in principle could host these Z3 parafermionic modes. So the question to the question whether we can get these Z3 out of purely fermionic models is yes, even though we still have a lot of work to understand the different phases of this model. So with that, I'd like to thank especially Rafael Levy, my PhD student, who's defending this tomorrow, actually. And some students in my group. This panel is outdated. We have Mateus here. It's also a new addition to the group. But thank you all for your attention.
So thank you, Luis. We have questions. I have a question, actually. Okay. So how would you experimentally realize this chain? Okay. What would be the requirements to get something?
All right. So let's start with the easier one, which is the Z4. Okay. So you would have to induce some sort of proximity pairing in a system where you would have a P-wave type of superconductivity, like in the current models for the Majoranas. So just to put this into perspective, this has not been done yet convincingly. I mean, there are many proposals to get just these two first terms, right? Then, of course, you would need strong interactions. So you need perhaps to engineering. I think the easiest way would be, try to engineer that in an optical lattice, where in principle you have all the handles on the interactions between different sites. So and you had to really fine tune the times of interaction that you have. So for now, especially in a model like that has preserves parity and everything is fine, I think the best way it's either optical lattice or you go back to what people have realized or believe that these parafermions live on is fractional quantum Hall states. That's the other, in terms of materials, I would go to fractional quantum Hall states where there is believed that they have quasi-particles which have these properties in some of the fractional plateaus.
Hi, Luis.
Hi.
I have one naive question. And when you analyze the coupling to the quantum dot, is there an easy argument of why both phases have a very similar behavior, just different amplitudes?
Okay, so that's a very good question. And there's some work that Edson Werneck and I did some time ago, and Carlos Eggs as well, that we understand that if you have just a Majorana mode here at the end of this chain, and you attach a quantum dot to it, the Majorana tends to migrate into the dot. So that changes the spectral properties of the dot just because they're coupled. Even though the dot is not in the topological region, because these quasi-particles at zero energy, it tends to easily leak into the dot. And that changes the spectral properties of it. So whether you have Majoranas here or whether you have some other topological zero mode, it also leak into that. So that's why in the trivial case where you have nothing here at the end, you have zero. But once you have something topological there, it leaks. Now, the thing is try to differentiate which one is leaking, like the Z2, the regular Majorana, or the parafermion. So that's the hard part is to differentiate between blue and red in an actual experiment.
Okay, so let's thank the speaker again. Oh, do we have another question? Yeah.
Okay.
No, thanks, Liz, for this nice talk. So I would just wonder if you try to characterize it I mean, you're just looking at gaps, right? So that's how
Yeah.
you. So
Yes.
did you try really to characterize the phase like via some topological invariant or some degeneracy of ground states? I mean, just to be sure you really have. I mean, they are really different.
Okay, that's a good point. We didn't because we trust the mapping. The mapping tells us that if we start in the topological regime of the Kitaev chain, and you don't leave there, the chair numbers and the topological invariants would be the same. But it would be a nice, say, consistency check to go back into the fermionic model and recalculate those things and see that we get the same numbers. The thing is that now it becomes much harder to calculate. It's much easier to calculate in the per fermion basis. So, but yeah. Okay.
Let's thank the speaker again.
Okay, thank you.
So the next speaker is Eric Andrade from the University of São Paulo. So Eric is going to present on perturbing the Kitaev model.
So thank you very much, Alex, for this invitation. I thank the ICTP for hosting this satellite meeting of the March meeting. It was a pleasure to be here. So I'm also discussing about Kitaev model, but this is a different Kitaev model. So, and I will benefit from both Gustavo and Luis talk. So, I mean, this will have Majorenas and spin orbit coupling. So I hopefully you enjoy it. So first things first, I'd like to thank my collaborators of which I've been doing this Kitaev business. So there is the people in Dresden, William, who is a former student in São Carlos, and now it's going to assume a position at Unicamp. There is Rodrigo and Eduardo here from Brazil, and there are the former students from the group which were with me in São Carlos, and they have moved somewhere else. In this talk, those are just recent reference, work which I did in this topic. So I mainly be focused on this work which you published with Vitor last year. So just in the interest of time, so I'll just be discussing this one. So first, I'll be talking about Mott insulators. So let me just spend 1 minute trying to discuss which kind of system we are talking about. So usually, so can I? Não, é porque está aparecendo. Só tirar essa coisa aqui do... Será que pode fechar aqui? E esse do Márcio jogar para... Okay. So sorry for this brief interruption. So I was just talking about interactions and how do you get a Mott insulator. So mainly talking about half-field systems with half-field band, which means 1 electron per unit cell. So usually in this case, so if you do not have interactions or the interactions are weak, so you would expect to get a metal because I mean, your Fermi energy will be sitting in the middle of the band, so since it's half-filling. But you can think of now if you have interactions, which I mean by this local U here, which are Coulomb repulsion. So if you put 2 electrons at the same site, you pay an energy U So they try to avoid each other. And if this U is much larger than this T, which would be mimicking the hopping, or they obtain this to move around, so we would have some sort of Coulomb blockade, because if U is just too large, the electrons won't move around just because they have to pay U to be on the same site. So then they will become an insulator. It's called a Mott insulator. It's a different insulator because it's not due to any band structure, but it's really due to correlations. So what would happen, instead of have this metal, you would have a gap. So you'd open a gap, and this gap would be proportional to this interaction U. So this is a Mott insulator. So although it is an insulator, it's still a very interesting insulator because it's not featureless. So the charges are frozen because the electrons don't move around. So the charge degrees of freedom are frozen, but that's not all, because you still have the spins degrees of freedom. So this kind of Mott insulator, the spins degree of freedom are very much active. Actually, the low energy model for this system is the Heisenberg model, well, at least, or variations of the Heisenberg model. So mainly we'll be focused on spins degrees of freedom and in Mott insulators. So because of correlations, you localize electrons, but they still have spins, and you can just talking about spins. So that's the kind of system which I'll be focusing, and I'll try to describe them to you. So if you have this kind of, you can think about, you have this sort of general phase diagram. So this X here, I put those U, the interaction, and this I have a new parameter which I call frustration F. So if I just increase this U, so I increase the electron localization, just briefly explain to you. So and then I cross to the Mott insulator, and here I have magnetism. And usually I'll have antiferromagnetism because J is usually positive in these systems. So at least if you have one band. So, but then you can turn about this new parameter frustration. So this is the classical picture of frustration. So now imagine, because of some geometrical constraint, in this case, the spins are interacting in a triangle. So all three spins, they interact with the positive J, so they would like to be anti-parallel to each other. So this is clearly not possible because, I mean, you can only satisfy one of them links. So this is frustration. So in this particular case for the triangular lattice, there is a way out. So they just form this non-collinear state. So this is called 120 degrees. So this is interesting. But there can be more, let's say, extreme situations where this parameter F is large, so the triangular lattice will be here. So you can have this F really large, for instance, in the Kagome lattice, which is kind of a cool system, but I won't be talking about. When you cross from this, let's say, from this metal to a phase which we call spin liquid, which is a phase in where you do not have long-range magnetic order, but the spins are not paramagnetic. So they are in this new phase, so you have the absence of spins freezing, but you have also interesting properties. You have fractional excitations, which are not magnons, which would have spin 1. In particular, one fractional excitation we'll find is a Majorana fermion, so that's nice. So that I thank Luis for explaining the Majorana to us. These are generally, they do not have long-range order, they do not break symmetry, but they have a new concept. It's called topological order or non-local order, which is nice. And also you can characterize them using these entanglement measures, which is also interesting, but these I won't be discussing. But just to show you, this is a really nice field where you can combine several interesting ideas of physics. So the particular model which I'll describe is another model by Kitaev. Kitaev nowadays is very fashionable. He has several interesting models. So the Kitaev model I'll be discussing is a model in a Mott insulator, in particular in a 2D Mott insulator living on a honeycomb lattice. There are different variations, but that's the original one and still the simplest. So you imagine you have spins living on the vertices of a honeycomb lattice, which I show here. And for each of the bonds of the lattice, for each side, I have 3 bonds, let's say. I call X, Y, and Z, and I color them at different colors as I show here. So, and this model is a peculiar model in the following sense. So let's say along this X bond, only the X components of the spin interact. Along the Y bond, only the Y components of the spin interact. And along the Z bond, only the Z component of the spin interact. So if you want to think about spin model, is like an Ising model, but it's an Ising model where you have 3 copies of them, each one of them living at the different bonds. So the frustration here is slightly different as compared to the triangular case, because the frustration here comes really from this funky interaction. So because, I mean, if you have a spin here, it either would like to point along X for this guy, along Y for this guy, along Z for this guy. So it actually does not know what to do. So that's where frustration comes about. So this is actually this is the one of the most extremely frustrated model you can find. I mean, you can quantify it. But amazingly enough, so Kitaio figured out it actually has an exact solution to dimension. So this is one of those few models, or at least now it's actually a class of models which you can solve. This is actually an integrable system, so there is an exact solution, but it's actually simple. So to solve this, what you do, you introduce our beloved Majorana, so that's interesting. So what you do is actually you map your spins into Majorana Fermions. So those C's here are Majorana Fermions. You actually introduce 4 Majorana Fermions, so you have CX, CY, CZ, and also there is a C without any index. But then you have a problem, because if you're talking about spins, you have spin up and spin down, and now here have 4 Majoranas. So I have to take care of that. So what you impose what we call local constraints. So you have to, plus the map, you have to put this constraint. So because you have to throw out 2 different states from this 4-dimensional Hilbert space to a local 2-dimensional Hilbert space. So you have to apply this constraint, but it's interesting enough, you can do this exactly in this model. And basically what you do, so you have to introduce also some variables U, which we call link variables, which basically just pair up spins of with the same character, leaving different bonds. So that's more or less represented here. So at each site, I put 4 different Majorana Fermions, and I pair up the Majoranas with the same color at different sites. And by the end of the day, I just have 1 remaining Majorana, which will be able to, those are BDC, which will be able to hopping around this lattice, and the hop will be modulated by this U variable or this link variable. So that's how the exact solution works. Is actually kind of very interesting. But that's not all. So that's the first part of the problem. So I was able to map it, but I still have to deal with these U variables. So it's interesting that these U variables, the Hamiltonian commute with it. So it has actually, you can fix the eigenvalues to either +1 or -1. It actually defines a flux around the plaquette. So this is an interesting concept. So you have this product of spins around a given plaquette, which you can map as the product of U around the plaquette. So this variable U can be either 1. So I'm showing all these blue bonds, they have U equal 1, or you can have U equals -1. So for instance, here I have this bonds equals -1. So, and then if I go around this plaquette, I pick up a sign, so I have this flux is equal -1. So I paint them different. So in principle, you can have infinite different ground state configurations for these link variables, but I mean, people figure out that actually the ground state is the 0 flux, so in which you have actually do not have a flux. So the problem is kind of simple. It's just where we actually just have the old-fashioned graphene band structure with Majoranas. So it's kind of interesting, but there is a catch. So I mean, if you look to the density of states of the excitations, the excitation of the problems will be Majoranas. So those are not Magnus, so they are fractional in the sense. So now there you have the first characteristics of a spin liquid. But there's also something interesting, because I mean, if you're talking about now a physical spin excitation, so let's say you have a spin flip, so just flip a spin in your system, that's a physical excitation. To flip a spin, basically what you have to do, you think about, if you flip a spin, you actually flip a bond. And if you flip a bond, you create flux on 2 different plaquettes. So your spin structure factor, which would be what you would actually measure in neutron scattering, for instance, it actually has a gap, which is the flux gap, and above this gap, it has this structure. So actually you have two excitations in your system. You have the flux excitations and the Majorana excitations. So it's actually fractional, and this model is really interesting. You can even calculate these things exactly. So it's really interesting. One more nice feature of this model is the following. So if you apply a magnetic field perpendicular to the plane, so actually you can gap out this Majorana band structure with a graphene-like, and you create chiral edge modes or edge modes. So basically what happens is the following. So you create topological edge modes living on the edge of these materials, and they are interesting because if they are topological, they have interesting transport properties, but the transport properties here are more subtle because, I mean, as we're talking about, you have a Mott insulator, you cannot transport charge, but you can transport energy. So basically what you can measure is the thermal Hall effect. So basically you hit up this edge of your sample. So there is a gradient of temperature here. Because you have the magnetic field, you also, it interacts with the spin, so it makes this side become hotter than that side, so you also generate a perpendicular gradient of temperature, and you can measure, let's say, the thermal conductivity like that, and you can measure the Hall response, which will be associated with the transverse response, and becomes quantized. So this is it's actually the same idea of the integer Hall effect, but here it has to do with the thermal Hall effect. So this is a prediction which comes out naturally from this Kitaev model, so, and that would be a clear signature of this Majorana states living along the edge. So that would be an interesting thing to look up in experiments. So have also these Kitaev materials, they have, I mean, although this model is kind of strange because it's extremely anisotropic, there are interesting proposals, and the main ingredient, the key ingredient here is strong spin-orbit coupling, as Gustavo explained to us. So if you have strong spin-orbit coupling, you are in principle able to generate these strongly anisotropic models, and then to have strong spin-orbit coupling, you need, for instance, ruthenium, you need iridium, so although it's expensive, people have grown it, so it's interesting enough, so people can do it. So, and in particular, I'll show ruthenium trichloride and this lithium and hydrogen. They are really good candidates to have Kitaev. But the key point here, you do need strong spin-orbit coupling, so have to focus on these heavy materials. So those are the natural candidates. So this is just an example for alpha ruthenium trichloride. So people, you can grow this in lab. So actually, this is temperature, this is magnetic field. So at zero magnetic field, this compound actually orders, it has a zigzag order, an antiferromagnetic order, which means it's not purely Kitaev, because I mean, if you were Kitaev, you'd have just spin liquid, but it's not a spin liquid, it's zigzag. But if you apply an external magnetic field, something really interesting happens, because I mean, the magnetic field will Kant, this antiferromagnetic order, and eventually you'd expect the spins would polarize to enter in this, what you call polarized phase, which is trivial. But it's interesting, apparently there is an intermediate phase between the magnetic phase and the polarized phase, where people observe a topological response. I mean, how they observe? Well, they measure precisely the thermal Hall coefficient, and if you look closely here, so this is the thermal response as a function of field, well, the data seems to be at a plateau, which is close to the expected value. I mean, yes, it's not a beautiful plateau as a whole. I mean, it's still under discussion because, as you can see, it's kind of tricky thing. But I mean, at least gives us hope. There is some interest in physics, but there's actually a lot of debate going on. So it's not. I'm not claiming this is the proof, but at least it's good evidence that there is interest in physics here. But there are several subtle points which I won't discuss. But it's still, well, I mean, it's kind of plateau if I have kind eyes. And the compound which I'm going to spend the next 10 minutes discuss is actually this hydrogen, lithium, iridium, oxygen. It's also because of this, it's also expected to be a kind of Kitaev-like material, but it's even more complicated because, I mean, the ground state of it does not show long-range magnetic order, which in principle, okay, that's the first signature I would have a spin liquid, but actually it's more complicated because if you look to the specific heat, for instance, is actually diverging at low temperatures with a power law of square root, 1 over square root of T. And also, if you look to the susceptibility, it has a similar divergence. And if you look to, let's say, to the NMR relaxation rate, divided by T, becomes constant. This is what we would expect, for instance, in a metal where you have lots of low energy excitation. So actually, it looks like it does not order, but it goes to a state which is not the Kitaev spin liquid. So what we thought, I mean, several people before us also realized, okay, maybe you have defects here, homogeneities or disorder is playing a role, and can we try to understand this material using a Kitaev-like model or framework, but adding the extra ingredient of disorder. So that's essentially our motivation, and that's the model we study. So this is the Kitaev model written in terms of Majorana fermions, and now we start to think about it as an effective low energy model. So you start to add different terms. So we add this kappa term, which breaks time reversal symmetry and mimics an external magnetic field. And you can show here, this is just a topological index. In particular, it's the Bott index, but it works the same way as the Chern number. It's just more convenient to calculate in real space. So this, as soon as this cap is different from 0, you have a non-trivial turn, a non-trivial Bott index, which is minus or plus 1 depending on the sign of kappa. So it really plays a role of this magnetic field. And also I can add this kappa 3 term, which I show here. It's a kind of interesting interaction between third neighbors in a peculiar path. But the point of it is just a perturbation with preserved time reversal symmetry. It won't be too much important for what we discussed, but in principle, you can play around with this model, adding several different terms. And what we realized was the following. So if you add a vacancy to this model, which means you just remove a site, let's say a magnetic site for your problem. So here, I just removed the site here, which is kind of shaded here. Some really interesting thing happens, because, I mean, as soon as you remove this, the local flux configuration in this plaquette changes. Actually, as you remove a site, you bind a flux to it. So kind of you flip one bond. So by removing this site, essentially you bind a flux within this plaquette. So these people realized long ago, so this was work by Williams, Chalk, and Musner back in 2010. They realized this actually you change your ground state configuration, or flux configuration. It's kind of non-trivial. So by removing a site or placing a vacancy in the system, you bind a flux to this plaquette. So this will have non-trivial effects I will show you. And also there is an interesting fact, you leave some unpaired spins here, which they are essentially loose because, I mean, they do not have this guy here to talk to. So, and this is interesting because, I mean, if you now, if you are in this bound flux situation, which I show here with just two bound flux, basically, your let's say your impurity or vacancy state lives at finite energy and not at zero energy, what we would have in a zero flux state. So if you look to the density of states of the problem of the Majorana excitation, actually has two main features. It has this finite peak here, which would be this let's say this bound state live along the edge of these plaquettes. And also, but it starts to develop some low energy excitation just because, let's say, if they are too close to each other, they can overlap and generate this zero energy or low energy excitation. So the problem actually has two classes of low energy excitation, the zero energy and the finite energy. So we analyze both of them. So if you look to the zero energy, if you zoom up here, basically you can fit this of states by a power law. So it actually diverges as a power law, which is interesting. And by divergence as a power law, you can immediately calculate several physical observers. For instance, the specific heat will immediately diverge as a power law just because the flux is gapped. So the low energy will always come from this power law. And also, if you look to the spin susceptibility, it will also diverge as a power law, just because, I mean, you have, let's say, the paired spins will just have a Pauli-like response, which is exactly what we expect. But let's say that those loose spins, those unpaired spins, they actually do not have to pay a flux because they do not have this link. So they can flip and pay nothing, and the response is really due to the Majorana alone. So you can kind of get this power law. So this is the first hint that a consistent explanation for the experiment is possible in terms of this Kitaev material, just because you realize, let's say, if you put vacancies, you get the thermodynamics right. So this is one positive feature. We can kind of understand how to get a power law, but I'll skip this just in the interest of time. You can more or less understand how to generate a power law. And now I would like to spend 2 or 3 minutes discussing about the topology of this problem, which is interesting. So now I would like to focus on this guy here. So this would be the energy of the states which live around this vacancy because of having this bound flux. So as explained to you, this bound flux actually it generates these states which are localized around the defect but leave a finite energy. And now if you look to the, let's say, to the both index or the topological index, if you consider the bound flux state, so this X here will be the dilution, or how much you remove from your spin. So you see, it's actually really close to a spin to 1. And then if the dilution is large enough, then you deviate. So because, I mean, you start to lose you start to go away from your topological phase. So this value here is not an integer because I average over several samples to get a feeling of what this order does. But on the other hand, if you just have a zero flux, I mean, if you do not consider this important fact that the impurity binds a flux So you see it start to diverge, to move away from one essentially immediately as soon as you put some vacancies, just because it start to generate in-gap states, which in principle destroy your topology. So okay, the bound flux, so the topological invariant shows us that we do have some sort of robustness in the presence of disorder. And then we can look, let's say this quantity here is just a level spacing. It's an interesting quantity and it's convenient in this concept for the following reason. So if this guy has this particular value here, touching here, it means you would have some extended states. In our case, we understand this as an extended state. Living along the edge would be this Majorana mode live around the edge. I mean, these people have looked into this in different contexts. So you can really see that if you have really small dilution, and you really see this nice level here, and inside the gap you get nothing, but as soon as your dilution starts to increase too much, let's say it gets to 0.6 or 0.8, so you start really to generate extended states even inside the gap, so you mix with your edge states, and then you lose your topological index 1. So you can see things, so this is kind of more showing the bulk edge correspondence in a simpler way, and and show that our interpretation is consistent, that really this bound flux protects the topology in your problem. So here are my conclusions. So I showed the Kitaeva model is a nice playground for spin fractionalization. It has Majorana fermions and this flux. They may be relevant for 4G and 5D5 materials because, I mean, they have correlations and strong spin-orbit coupling. But extra terms are present in real materials, so we need to deal with them. So maybe I just show a low energy description. There are several ways of doing this. Where this is, the model do host spin liquid phase, but I mean the question whether you see them in experiments still an open question. I try to argue to you for this particular iridate here, inhomogeneities are relevant, and I explained that you can really have this really low energy excitations which have power law like response, and that you can understand in terms of a Griffiths-like phase. I mean, I didn't discuss this, but for the benefit the experts, I say it. And also, it's interesting that conversely, what you would expect in non-interacting topological insulators, actually the Majorana chiral mode, they survive dilution. This is essentially because of this flux binding. This has to do of correlation. So the expectation, if you have a correlated topological system, it should be more robust with regard to perturbation than non-interacting one. So thank you very much for your attention.
So we have time for questions. Actually, I have a question. So in the experiments, when you show the thermal conductivity, so there are two graphs. What is the difference between the two graphs?
Yeah, well, just like, it's just, so here, those are, so here, basically two different field directions. So let's say this is this direction, and this is that would be, let's say, -6 and +6, just to show that if you flip the field, the response should flip. So they're just showing it. And this here is just a zoom around this direction to try to convince you.
Okay.
You do see a plateau, which is kind of not so convincing. But the problem is, I mean, there are several issues here. Phono is the first one. But I mean, usually there is something which you call Hall angle, which is the ratio between these and the longitudinal response. Usually in the Hall system is really large because I mean, the transverse response is really large. Here is really small, so it's kind of on the limit of fluctuation and so on. So it's kind of not so easy, so that's why people are really working hard. But I mean, you really measure thermal response at like few Kelvin, right? So it's kind of that's part of why it's hard.
Any further questions?
So very nice. So you mentioned inhomogeneities or defects, vacancies, or I see some kind of symmetry breaking in this system. So can you use your model to get more details of what it can be, or where do you put this inhomogeneity?
So that's a good question. So our motivation is kind of loose because I mean, we say, oh, this has hydrogen. Hydrogen does not like, I mean, so light, it can sit anywhere, that generates defects. So that's the main motivation. So we didn't do anything so let's say so fundamental. So we just modeled the dilution like at let's say an effective level. So either put
disorder in the bonds, I mean, modulate the bonds, or just remove spin by put vacant. So we stood both of them. So, but it's just, let's say, at this effective level. And the motivation is just, oh, you have hydrogen, solar. I mean, you can do an experiment, people can see which kind of defect you have, but it's more inspired by, let's say, by the NMR results. But it's really, we didn't do it. We didn't do it. It's kind of, well, you know better than I do this stuff.
Let's thank the speaker again and move on. So the last speaker of this session could not be here presently, in presence, but he's actually sent his talk. Yep.
Hello everyone, I am Márcio Sampaio Loncillo, a postdoc researcher at Federal University of ABC in São Paulo, Brazil. First of all, I'd like to thank everyone who is watching and the organizers for inviting me to present this work. Enhancing molecular dynamic simulations of aqueous systems with deep neural network force fields.
Então, é que na verdade parece que o microfone dele. O Zoom não tá me deixando, tá vendo? Tem a opção Share Sound, ele não deixa clicar, tá vendo? Deixa eu ver se... O suporte mandou uma mensagem aqui. Please click audio checkbox while sharing.
Hello everyone, can you hear me? There is a problem in the video?
You're not able to share the sound, so there's no sound.
So I can try from here?
Yeah,
if you
okay,
want.
that's perfect. Yeah, if you can do that.
Yes, let's see.
Can you share your screen?
Yes, just a minute. Are you seeing my screen? Yes.
Yep.
Yep. Just I'm happy. Hello everyone, I am Márcio Sampaio Loncillo, postdoc researcher at Federal University of ABC, São Paulo, Brazil. First of all,
Márcio?
are you listening?
No, yeah, you have to talk. So you have to give the presentation yourself.
Okay, well, let's start. I am facing some problems with internet access here, but you can try.
Yeah.
Just a minute. So, sorry about that. I will just take my time here. So, good morning, good afternoon, good night for everyone who is listening. Today, I would like to, first of all, thank you, the organizers, for inviting me and you for watching. Today, I'll talk about this work, enhancing molecular dynamic simulations of ecosystems with deep neural network force fields. So I would like to extend my thanks to my collaborators who are listed here. Some of them are from Brazil, while others are from the Stony Brook University in New York. Both of them have been pushed this work forward of investigating the properties of water from machine learning potentials. So let's start with our motivation here. It's essentially concerned about machine learning potentials, a different topic that I'll talk today. Essentially, I will bring to you here some key ideas from these machine learning paper reviews, as this one, machine learning potentials for next generation of matter simulations. From these authors, the sentence that I highlighted here is this one: machine learning potentials with promises to reach the accuracy of quantum mechanical computations at a substantially reduced computational cost. I will explain this a little bit better later. The second one is from this paper, Machine Learning Force Fields. I highlighted here two sentences. The first one is, one of the most promising applications is the construction of machine learning force fields with the aim to narrow the gap between the accuracy of ab initio methods and the efficiency of classical force fields. The second one is such universal machine learning approximations are in principle unlimited by the quality and the quantity of the reference data us to train them. Both are important. Essentially, what I will talk about today is essentially about the second sentence, in such a way that I will talk what is the quality and the quantity of the reference data set needed to produce accurate force fields for liquid water. So just in summary, to explain this a little bit better, from molecular dynamic simulations, allows one to simulate large systems for a long time from the microscope point of view, but its success relies on the quality of the empirical force field employed. On the other hand, from ab initio molecular dynamics, they are limited to small sizes systems as presented here and for short simulate time, but it provides very accurate simulations based on quantum mechanical methods such as density functional theory, DFT. The machine learning potentials combine the quantum accuracy of ab initio molecular dynamics with the computational efficiency of the empirical force fields. And this method has been recognized as a promising alternative to underlying new physical phenomena and aid in the material discovery process. So essentially, I would like to stress the situations where this is really important from our previous work of our group. Essentially, they investigate the properties of water from different neural network-based molecular dynamics, from different eccentric correlation functions, and they show that the structural properties of water essentially does not depend on the system size, but the dynamic ones, as I'm presented here, such as the diffusion coefficient as a function of time, have a strong dependence on the simulation size and the time scale. As just to be more clear, they show here the diffusion coefficients for small systems, the dashed line, while for a large system, the solid line, and as you can see here, for the small system, there are some fluctuations, and D appears to be not converged up to 2 nanoseconds. For a large system, as I'm shown here, they seem to be only converged after 500 picoseconds. In this way, these results shows what is essentially important. We need to have large systems and simulate these large systems for a long time to reduce the errors or even to converge this quantity And this is only possible if the ab initio occurs by perform neural network or machine learning potentials. So we are essentially interested in deep neural network approach, which has been shown to be a versatile tool able to produce accurate force fields trained with DFT calculations. Just to be more clear, a deep neural network is a type of machine learning model that is inspired by the structure and the functional form of the human brain. From a purely mathematical point of view, neural networks are essentially functional form, whose the parameters are optimized by minimizing a constant function, and it can be approximate any type of function with a great interpolation capability. In this area here, what's good, that we do not need to assign a functional form to describe the intermolecular atomic interactions, and also we do not need to employ empirical data to build our neural network force fields. What we need to do is essentially to compute the DFT calculation for a small system, essentially in order to obtain the forces and the energy and the forces for these small systems as presented here. We train this data and then we are able to perform large-scale molecular dynamics. So what are essentially the challenge? It can be done, for example, by the use of DPMD kit code. However, there are some choices, the training parameters. For example, as presented here, what are the numbers of neural layers, the number of training steps. This essentially is considered as a user optimization, and there is a common sense in the literature. If you find a model that performs well on the test and the training data set, we find a good model. This is essentially not true for machine learning potentials. We always need to perform large-scale molecular dynamics to see if the machine learning is indeed well-trained. So what's the big problem is the following: the DFT calculation of the reference data set is highly computational demand. And since neural network force fields require large amounts of data, it typically provides high accuracy, we have a problem. In this way, have a deep neural network force field trained with less DFT calculations is a very important issue, and is what I will talk about today. Besides this, we are in particular interested in the microscopic comprehension of ecosystems that can be benefit from the computer simulations based on these machine learning potentials. Again, I would like to talk about this work. Essentially, this previous work shows an alternative way to produce accurate force fields for liquid water that use less trained data set that it was commonest in the literature. Essentially, what they show is that the sampling is the crucial step in such a way that the training data set should be sampled from uncorrelated structures, a sample with various systems conditions, as I am showing here. We first perform a classical molecular dynamics for a small systems at different thermodynamic conditions, for example, different temperatures and different densities. And then we perform these simulations long as possible and just select the uncorrelated structures from the radio distribution function, but choose those that maximize this distance, the Chern-Simons distance. We arrive in this case with 18,000 of uncorrelated structures. The next step is essentially to perform the DFT calculations, in this case for different exchange correlation functions. In order to obtain the energy and the forces, we are able then to train this data, and finally, the last point, we are able to perform large-scale molecular dynamics as presented here. So I am interested to investigate if we can reduce even more the size of this training data set, and we employ here in our analysis these kind of functional data sets. So in this way, what is our goal? Is essentially we want to investigate deep neural network force fields designated at the level of the DFT to describe liquid water, focus on the quality and the size of the training data set considered. In particular, we want to see the effects of the trained data set size on the coverage of the physical properties of water by performing neural network dynamics. What these 18,000 of frames snapshots means, right? We have a small system that we compute the DFT energy and forces. For example, in this case, is 64. We have one energy value for each snapshot and the forces of the all atoms. We split this data. This results in this number of trained data points. We split this data 90% for training, 10% for testing. We call this configuration as our 100% case, in such a way that by choosing this neural network topology in this way here, we find an accurate force field for liquid water. In our work, we always keep this ratio of the number of the trained parameters or the number of data over the number of parameters always bigger than 8. We perform our training by the use of DPMD Kikit codes together with LAMMPS to perform the neural network molecular dynamics. So just to be clear, this is what we call 100% is a neural network force field. And we want to see if we can obtain different neural network force fields with this DFT reference data. So in order to do that, we need to verify if we indeed have one correlator DFT data. So we did this by performing a K-cross validation procedure. Essentially here is for 10. Essentially this technique is used in machine learning in situations where the number of the trained data points are small, but in our case we use it to verify if the deep neural network approach, the potential depends on a particular partition of the trained data set. Essentially, we measure the accuracy on the test data fold by measuring the root mean square error and the mean absolute error on both, on the energy and the forces. And by measuring the deviation of these errors, we are able to see if the neural network depends on a particular partition of the trained data set. So in this way, we find the small numbers, meaning that we indeed have one correlated data set. So with this, what we want to ask is, what's the minimum size of the trained data set to obtain initial quality results? So in this way, we randomly select subsets of the trained data set ranging from 10% to 100%. 10% here means this number of frames. Essentially, we're scaling down both the training data set and also the neural network topology in order to keep this ratio always bigger than 8. Just to be clear, what we are obtaining is a different neural network force fields for liquid water trained with just different subsets. And we are able to ask from molecular dynamics simulations the properties of water. Here's just an example of how these potentials, defeated potentials works. A and B are from our 100% case, C and D for the 10% case. The x-axis here are the DFT reference data set, for example, for the energy in electrovolts per atom, and for the force in electrovolts per angstrom. The y-axis here are the predicted value. As you can see, we test the model on both these data sets, the training and the test data set. As you can see, we have more or less a straight line, shows that the models predicted are very accurate. And what we can do next is essentially to measure the errors between the reference data set and the predicted by the neural network. As I am showing here, in A, we have the energy values, the energy error values in millielectronvolts per atom as a function of the trained data set size. In B here, we have the force in millielectronvolts per angstrom as a function of the trained data set size. We measure the errors from both, on root mean square error and mean absolute error. There is a common trend here in such a way that there is an initial decrease in the errors values, as you can see here for these 4 curves. After the errors reach the value of 20%, they belong essentially constant, which means it does not, if we add more training data set, the errors not change, but this only happens because we are using one correlated training data set. So in order to illustrate that this is related to the quality of the training data set, we obtain a different neural network force field that I like to show here. Essentially, we built a different neural network force fields in order to show that the good sampling, select the reference data for the training process is a crucial step. In such a way, we built this neural network here from the data came from a short ab initio molecular dynamics, in the sense that they are very correlated. Essentially, about the amount of the data used is similar to our 50%. So in this way, we have more or less the same amount of the data as the 50% case, but they are correlated. As you can see here on the left side, we find that these models performs well. We find very small errors here, but this is not enough to ensure that we will be able to simulate the large system for a long time. As I am presenting here on the right side, is a pair correlation function, the oxygen pair correlation functions as a function of the pair distance. We show here in the black curve the results for the ab initio molecular dynamics, where the neural network was built, and the system works well only up to 20 picoseconds, in the sense that after that point, the system tries to make non-physical bonds between the atoms, and the energy is no longer conserved. In this way, the idea to show here is that we even have a large amount of data, but if the quality is not considered, we will not have a accurate machine learning potential. So I would like to show here the results for one correlated potentials obtained for different training data set size. And in our case, the only 10% works well for a large system at fixed temperature for a long time, as I'm showing here on the right side, on the left side, sorry, for the oxygen-oxygen pair, the pair correlation as a function of the pair distance. This result is also true for the other pairs, the oxygen-hydrogen and the hydrogen-hydrogen pairs. As you can see here, there is no visible difference between these observed properties. We also show here the scan ab initio molecular dynamics results for the literature, and both of them are in well agreement. In order to show these results in a better way, we show here the relative error with respect to the 100% case. Essentially, the error are fluctuating around zero. The only exception is for the 10% case, where we have a high error in this range, 3 to 5 and up to 6%. So next, we ask about the density. Essentially, we perform now NPT dynamics, where the number of atoms and the pressure and the temperature are kept fixed. And in order to obtain this equilibrium density, we simulate the system size at fixed pressure, at different temperatures. As you can see here, for these two deep neural network force fields, we obtain more or less the same density, which is in agreement with the literature results for the scan. What is interesting to mention here that we are able to simulate the ice density, the hexagonal ice, also known as the frozen water, in the sense that we obtain the correct ice density. But what's more important, that this information is not encoded in our neural network force field. We just encode one correlated structures, many water-water interactions, and then we are able to simulate this ice phase as well. So we also show here the results of the vibration spectrum for these two cases, and they show more or less the same pattern. On the right side here, I am showing the diffusion coefficient as a function of time for these different neural network force fields. Essentially, after the time increases, reduce its fluctuations, and after some point it converges. And the only case that presents a high deviation with respect to the 100% case is the 10% case, more or less 1,600 uncorrelated structures. So if this, I would like to be more clear here in this way, that if one would like to recover the water properties by these machine learning potentials, we should have at least something between 20 and 30%, more or less 5,000 of uncorrelated structures, in order to recover this the water properties. This is in sense really important in situations that we have, for example, ion-pair dissociation or the solid-liquid interface, and we need to recover the right properties of water. So I want to conclude, the water, essentially we find the structural properties of water are less dependent on the size of the training data set compared to the dynamics one, in our case, the diffusion coefficient, and the correct sampling, the uncorrelated structures that provide a good distribution over the phase space allows one to significantly reduce the amount of data and the size of the neural network required to have an accurate neural network force field. This work has been published recently. Please, if you have any further questions, please send an email to me. I just like to point out some future and some current research. Indeed, we find a minimal size of the amount of the data needed to produce accurate force fields for water. And the question now is, how do the human choices, essentially the training parameters, impact on the quality of the trained machine potentials? That is not clear. If you change the number of neurons, layers, cost function, how will change. Always what is mentioned in the literature is about the quality and the quantity of the trained data set. But we are not sure about this, how these choices impact on this quality. The second, we are investigating the role of nuclear quantum effects on the structural properties of the hexagonal ice. We are interested to see if our neural network models built in this way for uncorrelated structures are able to simulate other ice phase. And also, we are investigating the ion-pair dissociation in water. So with this, I would like to thank our funding and you for your attention. Thank you very much.
So do we have questions? Okay, so if there are no questions, I'm not going to ask a question because I'm in this work. So if there are no further questions, then we'll thank all the speakers of this session, and we reconvene in a virtual session in 30 minutes. Thank you.
energy. For example, I brought here 2 pictures where we can see the importance of studying this interface. Here we can see how our full cell works atomically, and on another picture we can see an electrical current applying 2 electrodes and controlling a chemical reaction. So despite of the difference of this process, the main point here is that in the 2 processes, the water-metal interfaces is crucial on the mechanism and also on the efficiency of this process. However, there is characterize this interface is a challenge, and especially in on the interpretation and also on the understanding of this process. So, has some experimental results show that the potential challenge orientation picture where the water molecules tends to point towards electrodes for negative potentials, and for positive potentials, there is a tendency to the water molecules point away from the electrode. Especially in this work that I showed that, the authors characterized the structure of the water-metal interface using a vibrational spectroscopy. So they observed a lack of hysteresis, where they associate this effect to an oxidation surface. And in this sense, the effect of the difficulty to the interpretation of these results, we use computer simulation to in fact understand this interface and simulate the behavior of the water molecules under a bias condition. So, in this work, we showed that the authors characterized the behavior of a water molecule adsorbed on a gold surface, and showed that according to the bias, the sign of the bias, the molecules tend to or attract or to repel to the surface. But what about the vibrational properties? How does external bias potential change the vibrational properties? With this question in mind, we extend this previous work and investigate the effects of the bias on water structures, and we vary the voltage in a range of -5 electrovolts to 5 electrovolts. And in order to do that, we analyze how the bias potential change the water-metal interactions, and also how the external bias potential change the water-water and the water-metal interactions. In order to do that, we measure the geometrical properties and also the vibrational properties. So here we can see what happens to the water molecule when we apply the bias potential, the maximum bias potential. And here we can see how the tilt angle and also the distance is affected by the bias potential. So we can see that for positive potentials, the molecules tend to repeat of the surface, while for negative potentials, the water molecules tend to be attracted to the surface. And also, we can see the strongly effect on the tilt angle. And we also characterized the electronic structure, where we can see here the effect of in the charge difference density for positive and negative bias. And also, we can see here a symmetric effect. What we mean is that the effect of the positive potential on the molecule is different for the negative potentials to the molecule. Here we can see also the polarizable surface, the effect of the bias potential, and also that the charge density is proportional to the voltage applied. And now we can investigate also the vibrational properties, and we can see the vibrational properties is related to the changes on geometrical structure. So here we can see that for negative potentials, there is an increase of the vibrational values, while for positive potentials, there is a decrease of these values. So once we characterize the behavior of the water molecule adsorbed on gold surface, we characterize how how this potential can change the water-water interactions and also the water-metal interactions. So we used a H-down layer adsorbed on a gold surface, and here I show the effect of the potential in the flat molecules. Once the effect of the down molecules was so small. So here we can see that the effect of the bias potential is mainly on the flat molecules. As we can see on the molecules, just the molecules, we see here the asymmetric effect and also the tendency of the molecules go away from the electrode for positive potentials and approximation of the surface for negative potentials. Here we also characterize the vibrational properties, and here we made a uniform distribution of the values. Once here we have some values, not even more, 3 characteristic frequencies. And for negative potential, we can see that the frequencies join together in a central value. Once that for positive potentials, the frequencies split in characteristic values. We can see that on this graph, where we have for the negative potentials approximation of these values and also a decrease of these values. And for positive potentials, we have an increase of the frequencies of stretching and also the separation of these values. Here we can also associate the frequencies in its chains to specific molecules. So, for example, we have that the highest values of frequencies is associated with the flat molecules and also with asymmetric vibrational modes. While for the smallest values, we have that it's associated with the flat molecules and associated with the symmetric stretching vibration. So we characterized using the non-equilibrium screen functional and the DFT formalism the behavior of water molecules adsorbed on gold surfaces. And we saw that the molecules tends to approach to the metal when it's negatively charged, and we saw the opposite behavior for positively charged. And also, we observed asymmetric behavior of these structures associated with the interaction between the water and the metal. So, thank you for your attention, and this work was supported by FAPESP.
We have questions?
Luana, thanks for your nice talk. I have a question about you showed all these potentials, and I was wondering, to get these shifts in the Raman vibrational modes, do you get a very large field gradient at the surface? Because I suppose that the stretching is coming from, you're actually bending the molecule, right? So at what scale, spatial scale, the electric fields are varying, right?
We didn't do the Raman shift. We just calculate the frequencies by finite differences by diagonalizing the matrix force. And so, but the effect of the bias, we can measure the electric field felt by the molecule, and it isn't so bigger. But with this small electrical field felt by the molecule, we can see these changes. I don't know if I correctly answered.
Yeah, we can discuss later on the details. Thanks.
Okay, sorry.
Any further questions?
Do you have an idea of, so you presented that they tend to approach or be deflected by the surface, but do you have any idea on the type of potential, like what is how it depends with the distance of the molecule to the potential, to the surface?
We started with the, first of all, we optimized the structure with zero bias, with no potential. And after that, we analyzed how the molecules changes when we apply the potential. So this graph is after the optimization with the applied bias. I don't know if I answered correctly.
So I was worried. Well, not worried. I was asking like if you know. So basically, how the force of the surface acting on the molecule depends on the distance of the molecule to the surface.
Yes. Even we can see a uniform behavior after some bias. I don't know.
So can I answer that? So the typical change of distance is very, very tiny. I mean, relatively small. So the molecule is still bonded to the surface. So it's of the order of tenths of angstroms. That's the typical distance. Any further questions? So if not, let's thank the speaker again and move on. So the next speaker is Enésio Marinho Jr., and the title of his talk is Photovoltaic Efficiency of Bulk Transition Metal Decalcogenides by Ab initio Excited State Methods.
Hello, everyone. Can you hear me well? Okay. So thank you, the organizers, for this opportunity to talk about my work here. I am a postdoc here in the group of Alexandre Riley here in IFT, and we are working for research and talk about optoelectronic properties of some important materials. So here I will show you some results on the transition metal decalcogenides, and then we are essentially applying the excited state methods to describe the optoelectronic properties, and afterward we try to extract the photovoltaic efficiency of these materials. So as a brief introduction, we have some important materials which comprise a family called van der Waals materials. from which the most famous one is the graphite, and it's single-layer graphene. And we have many, a wide range of electronic properties. So we have metallic and semi-metallic materials, such as graphene and others. We have semiconductors, such as black phosphorus and metal dichalcogenides. And we have some insulators, such as the boron nitride. And these materials have been applied in many important devices, so optoelectronics, solar cells, and sensors, and so on and so forth. So essentially, the transitional metal dichalcogenides are van der Waals materials of type MX2, where M is a metal and X is a chalcogen atom. To date, we have more than 40 materials, 40 transitional metal dichalcogenides. And within this class, we have also many properties. So we have some semiconductors and insulators. We have some semi-metals, and we have metals, true metals. And although many of these technologies try to explore a single layer of these transitional metal dichalcogenides, we have some examples in the literature that try to explore the few layers of these materials to fabricate some solar cells. So here we have an article that produce a Schottky solar cell using transitional metal dichalcogenides. Here we have an example of flexible solar cells using transitional metal dichalcogenides. So essentially here we are trying to explore the optoelectronic properties of these transitional metal dichalcogenides by means of GW and Betz-Salpeter, that is the standard, the state of the art to describe these properties. And therefore, afterward, we try to explore the photovoltaic efficiency of these materials, employing the so-called SLME, spectroscopy limited maximum efficiency for these materials. Briefly, we have, as our theoretical framework, we already know that applying the standard Conshan DFT, we have the so-called band gap problem for this approach. As we can see here in these red squares here, the band gap tends to be underestimated when we compared to the experimental for many semiconductors. And then we need to apply a more reliable, a more suitable framework, and then we know that the many-body perturbation theory provides good results for this issue. So the main quantity in the many-body perturbation theory is the Green's function. And important to say that in Green's functions, the poles represents the true many-particle excitation energies. And okay, so but how can we get these Green's functions? So we start using the Dyson equation. So the Dyson equation, the first term is the non-interacting Green's functions. But the second one, we have the self-energy operator, which is a non-local and energy-dependent potential. This is an also important amount here in the many-body perturbation theory. And then in 1965, Lars Hedding has proposed a self-consistent method to get to obtain the self-energy in the so-called GW approximation, where we apply not only the self-energy, but the Green's function, the polarizability, and the screened Coulomb potential, and we neglect the vertex function, and we described the self-energy as an integral of this product of the Green's function and the screened Coulomb potential. And at the end of the day, we can calculate the quasi-particle energy correction for the Conshan energies applying this quasi-particle energy like in this way. And also within the many-body perturbation theory framework, we can calculate the optical properties of some materials, including the excitonic effects in this. So we can solve the Betz-Salpeter equation, which start from the two-particle Green's function, and applying some approximations, we can describe this equation like an eigenvalue problem like this, where the Hamiltonian contains a single particle energy difference plus the so-called Betz-Salpeter kernel here. And so we can calculate the absorption spectra as an imaginary part of the dielectric function. We have here the dipoles, the volume of the system, and then we use the exciton eigen function here, actually is an envelope function here, and exciton energies. And then our results, first we obtain our relaxed destructors within standard DFT calculations. We are using quantum espresso, including van der Waals corrections and spin-orbit coupling in all the calculations. And we are studying essentially 4 materials. So molybdenum disulfide, molybdenum diselenide, tungsten disulfide, tungsten diselenide in the bulk phase of these materials. Here I present some details of our calculations. We are applying essentially the PBE functional, and we have good agreement with the crystal lattice as, when compared to the experimental ones. And here is some of our results on the convergence tests of the GW calculations. This is an important part of these calculations, since we have many features to be converged. And here I am showing essentially the quasi-particle gap error as a function of, for instance, number of bands in the correlation part of the self-energy, and the K-grid in this graphic. Important to say that we are using the YAML code for these calculations. And here I'm showing you the quasi-particle bond structure for example, for the MOS2 material. We are, as we can see, this is a indirect band gap material as expected for the bulk phase. The single layer of these materials tends to be direct band gaps, but the bulk phase tends to be indirect. So this is well described using, in blue we have the GW calculations, and in dashed lines here we have the PBE bands. And here I present the results of the fundamental band gap, which are better described using G0 W0 when compared to the PBE. And now talking about the Betz-Salpeter equation, the optical spectra, we here as a test, only showing the tests for the molybdenum disulfide. We have converged all the main features for the Betz-Salpeter equation as well. And here is the results of our convergence tests. And then here I'm showing you the optical spectra of the 4 analyzed materials here. So as you can see, in blue we have the Betz-Salpeter optical spectra. In orange we have the independent quasi-particle, which not include the excitonic effects. And we can see a good agreement with experiments And we also can see that the excitonic effects plays important roles for the optical spectra of these materials. And at the end, we try to explore, to compute the photovoltaic efficiency of these materials, applying the spectroscope limited maximum efficiency and also the Shockley quasar limit. Essentially, the Shockley quasar limit used the band gap of materials, and the SLME used the thickness and the standard solar spectrum as well. And in this LME approach, we have the reverse saturation current being described like this. So we have the radiative term here over this Boltzmann term, where this delta is essentially, in our work, is essentially the optical band gap minus the fundamental band gap. And here we have the results of the theoretical frame, the theoretical photovoltaic efficiency. Essentially, we can see that the selenide materials tends to present a higher efficiency when compared to the sulfide ones. And here I am comparing the photovoltaic efficiency within these two approaches. And that's it. So as a take-home message, the GW plus Betz-Salpeter provides an accurate theoretical framework to get the optical electronic properties of these materials, and the SLME can be applied to estimate the theoretical photovoltaic efficiency of these materials. So this is our team. So Professor Alexandre, Professor Pedro Venezuela, Professor Cesar. Thanks for FAPESP for the funding, and Grid Unesp and Senapad for computational resources. That's all. Thank you.
We have time for one quick question.
Thanks for the nice talk and nice work. So I was just wondering, you showed comparison between the experimental gap and the theoretical gap, but how about this efficiency you just calculated? I mean, do you have some experimental estimative to them? I mean, how well do they compare to the experimental values, the efficiencies?
No, the efficiency. If you have any experiments that measure the efficiency.
Okay. We have. It's hard to compare, since we have in experiments we have applying some structures and heterojunctions. So, but I'm trying to explore, and then, for instance, for the tungsten selenide, I have shown an efficiency of about 40%, which is the higher one that but this is essentially an upper limit in experiments. This is.
Okay, so let's thank the speaker again, move on. So, the next talk is going to be given by Sabari Subramanian. Did I say it right? Yeah. Study of, so you said it's wrong, but it's fine. Okay. Yeah. Thank you. So it's a study of quantum turbulence in dipolar Bose-Einstein condensates by circularly moving laser.
Thank you. So I am Sabari, working as postdoc with Professor Laura Tomio. First, I thank the organizers for this opportunity. Is it audible? So I'm talking in English, okay. So title of my presentation is Quantum Turbulence in Dipolar Bose-Einstein Condensate. This is the outline of my presentation. First, I will give some short introduction about the Bose-Einstein condensate for the beginners or the general audience. Next, something about some notation about the turbulence. Then I will explain the theoretical model, which I'm going to discuss in my work. Next, I will discuss 2 cases of results. So the part of the results are already published in these papers. So we all are known about the 3 states of matter, which we use, experience in everyday life. Solid, liquid, gas. One can distinguish easily by changing the temperature. For example, if you have the water, if we heat up, if we increase the temperature, then it will evaporate, which means it is in the gas form. In the same way, if you reduce the temperature of the water, like if you keep the water in the refrigerator, it is in the solid state in the form of the ice cube. So from this, we can understand that one can change the states of matter by temperature, by varying the temperature. So what happens if you increase the temperature like million, billion degree Kelvin? So yeah, everything will be in the plasma state. The example of plasma state is the sun. The temperature of the inner part of the sun is around 1 million degree Kelvin. So same way, if you reduce the temperature close to absolute 0, what will happen? So in 1924, Indian physicist Satyendranath Bose proposed new statistics for the massless particle. And Einstein extended this approach to the massed particle, and they predicted that at very low temperature, large fraction of atom should occupy in the lowest quantum state. It's called Bose-Einstein quantum state. So the interesting thing is how to reach this very low temperature. They are used 2 cooling methods. One is evaporative cooling, another one is, first one is the laser cooling, another is evaporative cooling. Which one? Yeah, using laser cooling, they reach from room temperature to microkelvin. Then after that, using evaporative cooling from microkelvin to nanokelvin, where they achieve the BEC. This is the Bose-Einstein quantum state. So in laser cooling, they use 6 laser beams in all 3 directions. So in the center, we have atoms in room temperature. When atoms moves towards the laser, when it absorbs the laser, then it kicks from the back direction. Then it gets reduce the kinetic energy. In this way, in all 6 directions, the kinetic energy of the atoms get reduced. So like this, it reaches up to the microkelvin. After that, they use the magnetic field to trap the atom's center of the chamber. By tuning the trapping frequency, they allow to escape the atom, higher energetic atom, from the trap. So in the end, we have only very low energy atom. This is how they reach. This evaporative cooling. This is how they reach nanokelvin. When they reach nanokelvin, it is already in Bose-Einstein quantum states. So what happened when we reduce the temperature, what happened into the atoms? When you reduce the temperature, the atom feels when you reduce the temperature, the wave nature of the atom is increased. So the wave nature of the atom is this one is the de Broglie wavelength. So the wave nature is the de Broglie wavelength is inversely proportional to the square root of the temperature. So when we reduce the temperature, the wave nature is increased. So here is in the form of a particle, in the form of wave here. So in the room temperature, it's like a billiards ball and with the different velocities. So when you reduce the temperature, the wave nature increases. Then at certain time, it starts to overlap. And close to some nanokelvin temperature, almost it's a single wave like this. A single wave, and here is indistinguishable particle. It becomes indistinguishable particle. Here maybe, I think, it's the end. Oh. Okay, so in this movie, it is they have given how the wave nature is increased when they reduce the temperature like this. Yeah, yes, but it will take time, I think. Maybe when we reduce the temperature, the energies get reduced, and also the wave nature is increased. And the end, it's one single system, inducible single system. So turbulence. In fluid dynamics, turbulent flow is characterized by the chaotic changes in the pressure and flow velocity. It is in contrast to the laminar flow. Actually, the laminar flow occurs when the low Reynolds number. Also, where in this case, the viscous force are dominant. But in turbulent flow, where the higher, when turbulent flow occurs in high Reynolds number, where the inertial force dominate, these inertial forces tend to produce instabilities and eddies and vortices. So when you have the turbulent flow, we will have this kind of moving vortices like this. So in our everyday life, we are experiencing a turbulence and a laminar flow. So for example, when you open the water slowly, the water flows smoothly. There is no interaction, the layer interaction. When we push, then it mixes together, then this layer, it's in the turbulent flow like this. You can see, not only here in the water, so also in everyday life, you can see surf and river in the water in the river. When we are near the dam, it is high turbulent, high Reynolds number with, and storm clouds, smoke from the chimney like this. So when we expect the turbulent, when we have the moving vortices with the different sizes, which with the interactions, we will expect some turbulence. So here is few list of few applications. We are using every day, everywhere we are using the turbulence, from agriculture and aircraft and rockets, interstellar space, maybe everywhere. Yeah, suppose if we paint this wall, we are using the turbulent, filling the air in the car and cleaning the cars and bikes. Everywhere we are using the turbulent technique. So here is some difference between the classical and quantum turbulence. The left side figure is the Jupiter's Great Red Spot. This range is around 10,000 kilometers. The right side is the quantum turbulence, around 0.1 millimeter. These vortices are due to the puddle potential. This table shows some similarities and difference between the classical and quantum turbulence. For example, I will show one or two similarities. The similarities are the turbulent type. Both in classical and quantum, we have the hydrodynamic and wave turbulence. And one more maybe homogeneous in both the classical and quantum. Here, along with the homogeneous, also we have non-homogeneous. And differences may be some distributions in classical is the viscosity and quantum is sound waves. There are many similarities. I listed only few. And these are my model equations, where the dropping potential is the combination of the harmonic plus the time-dependent Gaussian obstacle. The harmonic potential used to trap the system and the Gaussian obstacle used to stir the system to generate the vortices. This part is the radial part and this axial part of the trapping potential. So this is the Gaussian form of the Gaussian potential. I will explain this later. And this system, we have two kind of interactions. One is the short range contact interaction. Another one is the long range dipolar interaction. This short range contact interaction depends on the SOS scatter length AS and the number of atoms and also mass of the atoms. One can tune this SOS scatter length experimentally by Fishbach resonance technique. And the dipolar interaction is this, the form of the dipolar interaction is. Here R is the interparticle separation between the dipoles. And the coupling constant CD is this, and it depends on the permeability of vacuum and times square up the permanent magnet dipole. And one can tune these dipole interactions. So here, the left side figure is the non-polarized dipoles. The right side is the polarized dipoles. This angle is the angle between the polarized angle and interparticle separation. So when theta is equal to 0, we have the head to tail configuration. It will attract each other. When it is 90, it's a side-by-side configuration, so it repel each other. So when we have this configuration, two configuration, we will have two kind of system. One is 1D, another is 2D. From this in 1D, due to the attraction, it get collapse easily when compared with 2D. Because in 2D, we have the side-by-side repulsion, so it stays more stable. So further, we can tune this dipole along the polarization angle like this, with this angle. So like this, when we have this 0, when the pi is 0, then it is repulsion. When pi is 90, it is attraction. So by tuning, why I'm showing this, I'm going to show some results by tuning this and versus this dipole angle by versus this speed of this Gaussian obstacle. Here Vt is the amplitude of the Gaussian potential. It's a time dependent, but in this study, I'm going to discuss only the time independent. So it's height of the Gaussian obstacle, and width W is the width of the Gaussian obstacle. Where x naught, y naught is this form, and mu is the frequency, and epsilon is the so epsilon is the distance from the center of the distance from the center. So I have considered these two cases. One is the circular motion, another one is the linear motion. So see here the x-axis is the velocity of the Gaussian obstacle, and y-axis is the tuning of the dipole-dipole interaction. So I have observed three ranges. One is no dipole, no vertices, and another one is vertices with in the form of dipoles, and another third one is the vertices in the form of clusters. So I'm going to show some, for in the three region. So in the first row is there is no vertex emission. In second row we have vertex emission in the form of dipoles. Third row vertex emission in the form of vertex clusters. So you can see maybe better in the 3D view. I have time, okay. So I have some results. So from the angular momentum, so from this, when we change the dipole angle, we will have only small changes in the angular momentum. But the angular momentum changes when we change the velocity of the obstacle. So the first two is the difference between these alpha, and this one is the difference between the speed, velocity of the obstacle. The similar kind of effect observed in kinetic energy of the system also, and some current density and torque of the system. So further, I look at the kinetic energy in the form of compressible and incompressible part. So this kinetic energy is mostly affected by this compressible part. We can see this. This you can see the incompressible part gets some stable after some time, but the compressible part is always increasing. So this effect of this one, it's always increasing. One case I just explained, all three cases I have shown. Okay, I'll stop here. So I have one more cases, then I need some more time, that's why.
Thank the speaker again. We have time for one quick question. Okay, I have a question. So when you move and you get turbulence, would you say that you destroyed the condensate or not?
Yeah, when we move some particular speed, then it will destroy. But here we have some
We
limit.
still have some. Okay.
So I just thank Alexandre also, when
okay, thank you.
Move the chair from one half session to another half session. So please, Mariana, come to take your part. And Mariana Stoher is also wrong, the pronunciation. Okay, it's good, Stoher. And she'll talk to us a little bit about contextuality in independent, theory independent, or context incompatibility. So just remind you all 12 plus 3 minutes for us to have discussions.
Okay, so good afternoon, everyone. As they have mentioned, my name is Mariana Stoher, and this work was supervised by Professor Renato with great contributions from Professor Ana at the Foundations of Quantum Mechanics group at UFPR with financial support from CAPES. So first things first, why we study incompatibility. And we know that incompatibility is a characteristic that only arises in quantum systems. So there's no classical counterpart for it. And as such, incompatibility is related to some very weird quantum mechanical effects, like the violation of Bell inequalities. The experimental proof of those violations actually won the Nobel Prize last year. So clearly, it is a big deal. And yet, incompatibility, there is not a single definition, there is no single approach, and no single interpretation for it. So I'll show a little string of relevant definitions, starting with the most common ones. If you ever heard of quantum mechanics, there's a good chance you've encountered them. So commutativity and uncertainty relations. Those two definitions are used to categorize two observables on compatible or not. And when I say observables here, I actually mean projective observables, because for the next two definitions, I'll be speaking of POVMs. You don't need to worry about this too much. All you need to know is that POVMs are a form of generalized measurements. So for POVMs, I've brought joint measurability, which is the definition that says, given two POVMs, they are jointly measurable or compatible if there exists a third POVM that can generate the first two. And also, I've brought non-disturbance. For this, I also need the concept of a quantum instrument. But again, you don't need to worry about this. A quantum instrument is just a quantum channel that implements the measurement of a POVM. So you have an input state, and the output is a non-normalized state that has been measured in the POVM of choice. So the definition is, if you can implement an observable A through an instrument, and this does not change the probability distribution for a POVM B, then they are compatible. And actually, the only reason I've brought all of these definitions is to ask about the role of the state in them. Because see, in classical mechanics, there is no incompatibility, right? So you can measure position and momentum, no problem. But now, if you take a quantum system with the same set of position and momentum, incompatibility would be a problem. So clearly, the state that you're measuring has some influence on whether or not there is compatibility. And all of those definitions have little to no regard at all for the state. And we find this very counterintuitive, and it is because of this that they have proposed the definition of incompatibility of a physical context. A physical context is nothing more than the set of the measurements you're performing. Here, I'm back with projective measurements, and the state. So now you're speaking of a whole context being compatible or not. For this definition, I also need the concept of non-selective measurement map, which is nothing more than the idea of making a measurement, but not selecting a single outcome. So you're summing for all the possible outcomes. And this definition was proposed based on a protocol for detecting information leakage on a quantum communication channel. So we have our friends, Alice and Bob, and they are communicating. And Bob is expecting to receive this state right here. But maybe there's a spy, Eve, stealing information from this communication channel. And what Bob receives is this other map right here, which has less information. And we quantify the information consumed from the communication channel via relative entropy. I forgot to change the image right here. You can see it is a line instead of B, but I mean the same thing, okay? The important part is, in this definition, compatibility means there is no leakage. So this will only happen if the states you're comparing are the same. And in its turn, this relation between the maps will only be true for these three cases here. The first is if the observables you're using are commuting observables, which is great because we're saying that this definition includes commutativity. The second case is if the state you're measuring is actually the identity state, which again is very good because a state like this only has classical probabilities. And we're saying that this always leads to a compatible context. And there is a third case here, which is if Rho is an eigenstate of the second observable that you're measuring with the additional restraint that the observables are maximally incompatible. So it's a very, very specific case. I'll also be referring of this definition as MSA definition for the name of the authors, okay? And now what I want to highlight here is that all of those 5 definitions that I've brought, they are all built in very quantum frameworks. So it's always quantum observables, always quantum states, always quantum entropies. And we know that quantum mechanics is a very experimentally successful theory, but it is probably not the last word on the physical description of nature because there's still a lot of open questions, right? There's the whole gravitation deal, for example. And because of this, there's been an effort done to try to propose quantum mechanics through more basic and fewer postulates. So the idea is that you can maintain the successes of the quantum mechanical theory, but answer some of the open questions. And it is because of this that we wanted to propose a version of context incompatibility that is totally independent of theory, because we want to brace for whatever comes next in physics. To do this, we based our definition on probabilities and non-selective measurements, 2 very general things. And you might be wondering why non-selective measurements? And the reason is, since we're using probabilities, because we believe probabilities are very general, it makes more sense to not select a single outcome of a measurement. And non-selective measurement sums for all of the outcomes of whatever you're measuring. So that's why we use them. And I also brought here a little recipe of how non-selective measurements could look like in terms of probabilities. The idea is that you're measuring the physical quantity y on a preparation E. And you have the probability distribution for this. But say a colleague comes up and tells you, hey, I've actually already measured this preparation, but I measured the physical quantity x. So now you know that your distribution probability is a conditional one to the outcome that your colleague had. But he doesn't tell you exactly what this outcome was. So now you have to weight this by the chance of that outcome happening and summing for all of the outcomes that are possible when measuring x. And we can understand this as the probability distribution of y onto a preparation that already underwent the non-selective measurement of x. And in fact, if you plug in here quantum probabilities, you get what you expected with the quantum non-selective measurement map that I shown you before. Okay, so the definition itself. We are saying that if the non-selective measurement of y does not alter the probability distribution of x and vice versa for a given preparation, then those probabilities are true and the context is compatible. So this is very strong. It's a two-way relationship in the sense that we need both of those expressions to be satisfied for there to be compatibility. Okay, so we know that incompatibility arises in quantum mechanics. So we wanted to see how this behaves for a quantum context. So we got one exactly like the one for the MSA definition. We have projective measurements also. And when we plugged in quantum probabilities, we get these expressions here. There's two extra ones, and they are actually just Heisenberg's picture. So the important thing is that you need to satisfy one of the top and one of the bottom equations at the same time for there to be compatibility. And this will only happen if these relations between the maps are true. If you recall, MSA definition was very similar, but there it was a one-way relationship. So it was only one expression, and actually the order of measurement here is switched. So there it was phi BA, not phi AB. I'll speak a little bit more on the connections with the MSA definition in the future, because for now I wanted to see what kind of context could satisfy this. And I've brought an example, a case study of the qubit in the block representation. So here, the states, the observables, the maps, they're all vectors in this sphere. And when you apply the criteria, what you get is these two equations here, from which it's really easy to see there are three possible solutions. The first one is if R is 0, because then both of the equations will be satisfied at the same time. And this actually is the case where ρ is the identity. As we said, this has only classical probabilities, and we're saying that it always leads to a compatible context. The second case for satisfying the two equations is if gamma and eta are both 0. If you see the form for eta here, for gamma, sorry, you would see that if A and B are parallel, so this inner product is 1, then gamma is 0. And actually, the requirement of A and B being parallel is enough for eta to also be 0. So this is our second case for compatibility. And this actually is the case for commuting observables. So very nice. It includes commutativity as well. But there's also a third case here, which is if the cosines are 0. And we'll see that this happens if R is actually perpendicular to the plane formed by the two observables. So this third case seemed a little different, and we wanted to see if the MSA definition also included it somehow. To do this, we built quantifiers, both for the expression with the maps and the expression with the probabilities. For the maps, we used relative entropy, and for the probabilities, we used the Kullback-Leibler divergence. And actually, if you're using a quantum context, those two quantifiers are completely interchangeable. So I can prove this, but I've brought here a picture to showcase it. And every graph that I show will be done for the qubit in the block representation with 1 million randomized contexts. And the MSA definition was a one-way relationship, right? So it clearly will be weaker. And we built a two-way relationship for them. So we want to see if adding this term right here would be enough for their definition to be equal to ours. And we gave them also a divergence-based quantifier. But for them, those two are not interchangeable. And the divergence-based one is actually a lower bound for the entropy-based one. And you can see this in the graph right here. So it already hints us that those two definitions are not the same, and we can see it very clearly in the direct comparison. So you can see that the graphs have like a leaf shape, which is not unusual when you're comparing quantifiers. It just means that there is a relationship between them because the points are not all scattered around, but they are not exactly the same. I've checked numerically for even more than 1 million contexts, and they also always go to 0 together. So we are saying that they are equivalent, the definitions, because they agree whenever there is compatibility, but you can see from the graph that sometimes they will agree on the amount of incompatibility that an incompatible context has. So to sum it up, I'm so sorry, we achieved a theory-independent definition for context incompatibility in the sense that any probabilistic theory could use it. Our definition encompassed the expected cases of compatibility for 2 dimensions. It is equivalent to the other definition of context incompatibility, but ours comes with a completely interchangeable quantifier based on probabilities, which potentially is easier to implement on the lab. And this is exactly what we're doing next. We're looking for implementations. generalizations, and we wanted to see if we can find connections with some other interesting quantum effects like Bell non-locality and steering. So some additional references, and thank you.
Questions? No? So let me make one. It's very interesting, the idea of including states in the definition of compatibility and then contexts, but there is something that do not discuss well with this, that is the notion of state-independent contextuality.
Yes, I saw the name of the of the lecture, and actually, I mean, we know that there's some level of independence in some type of definitions, like if you're using position and momentum, for example, even in the uncertainty relation is independent of the state. So we think that in some level it is, but we are really looking into that like classical limit type of situation, you know? We want to include this line on the definition of incompatibility. Okay.
Fair enough. Let me collect the last question here, and the next speaker prepare himself.
Yeah, so in the same line of questioning of my fellow here, if I understood it, what you did was you included the state as part of the description of your contextuality, right? But
actually, I'm not speaking necessarily of contextuality, although I see the confusion because of the name context, right? And I actually, I've spoken with my advisor about this, but the context that I mentioned here and contextuality are two different things. The context is just the name that they gave for the set of the observables and the state.
Sure.
Yeah.
Fine, fair enough. But then my question is, from a practical point of view, wouldn't it characterize kind of a volume zero situation, in the sense that, like, if you have to be, so if for you to have the third condition in place, in most cases, at least that I can think of, like the one that you the example that you give, is one very particular state for one very particular A and one very particular B. If you change a little bit A and B, then you have to adjust the state, like your cosine of equals to 0. So in that case, it's a volume zero situation.
Yeah, it's very specific, this third case, but we actually think it's very interesting that it came up, because the two first are what we wanted in a way, and the third case, we actually thought because we weren't expecting it, we thought, oh my God, there is this whole set of states that for any two observables, there will be compatibility, because we weren't expecting it, so A and B can have any angle between them, let's say. And if R is perpendicular to the plane formed by them, then there is compatibility. I guess it's a point of view. Yeah, probably.
Thank you very much again, Mariana. And let us change to Lucas. Of course, the idea is that we stay here, we'll have a coffee break soon, and all these discussions should continue during the coffee break. This is the practical idea of having this session in between the other two. So I forgot my list, so I do not know the complete name of Lucas anymore. And please introduce yourself. Lucas Medeiros Ruela, of course I know, and he'll talk about fabrication and measurements on transmon type. superconducting qubits. Please, 12 minutes, Lucas.
Okay. Hello, everyone. Hello, everyone. I'm Lucas, and here I'm going to talk about a little my project, a PhD project here, which was and is fabricating and measuring a transmon. I'm from State University of Campinas, and the outline of this presentation is I'm going to talk about the motivation, which is working with nanoresonators, and then what I had to do first to get of the objective, which is get interaction between a transmon and a nanoresonator. So about background, we have here what we want to do is measure, observe the states, the occupation states of a mechanical nanoresonator, and with that, and we're going to do using a transmon. So here, here we have a qubit, which couples capacitively with the nanoresonator, and the full Hamiltonian of the system have terms given by the qubits, the electrostatic energy and the Josephson energy, as well as the energy given by the phonons of the modes in that resonator, and a interaction term, which is a dipole interaction. So basically we have a two-level system interaction in a harmonic oscillator. What we want is have a transmon as a quantum clock interacting with the system, and the idea would be similar to this work from Zlatan in 2019, where we have a qubit here interacting in a surface wave mode here. And the idea is to observe the precession of the qubits as it interacts with that system. Now, before we can actually do that, it's good to have a qubit, a transmon, working, fabricating in our lab. So what we set to do in the beginning of my PhD was master the techniques for controlling, measuring, and fabricating that system. Just a transmon coupled to a microwave cavity. So no resonator right now. And so here's the schematics of the system. Here's a microwave cavity and the qubits in the middle interacting with it. Here is an image, for example, of a part of the transmon. There's a Josephson junction missing here, which are necessary for a nonlinear system that forms the transmon. And here is that same two pads here, coupled to a microwave cavity. The idea is to interact, send pulses to the cavity, observe its states, and from that we can infer the state of the qubits. And the main regime that we are working is the dispersive regime. The milestone was to obtain two characteristic times from transmon: the relaxation time and the coherence time. Those gives us the time frame to send pulses and control that qubits, the quantum operations. However, when I started in my lab, we didn't have a working lab. So here's our boxes, all closed. I started here, and most of my work was on assembling that together with my advisor. We managed to get something working here, and even with many setbacks, the pandemic and broken equipments and everything that happens when you're assembling a laboratory from the ground up. To assemble the lab, you need many equipments. I help install here the cryogenic lines for the dilution refrigerator that we use to get for the below 30 milli-K temperatures that we need. All the amplifiers for amplifying the signals, which are so low. Here we also, I installed here together with my advisor, the evaporator that we use to get for the junctions, the Josephson junctions. We managed to get some really good pressures here, and we're really proud from that. Okay. Also, all the radio frequency equipments that we needed to measure and control the qubit radio frequency here, So here's the panel. Here's an example of the schematics that's happening here, where we control all those equipments with the trigger pulse that is controlled by the CPU, where we send many different pulses and check it back to get the important information from the qubits, which is basically the IQ, or the amplitude and phase return from the system. So we have an example of a setup that I did. All those are made in Python. The have codes are done in C. I programmed all that, all the drivers also. Here is an example of a down conversion heterodyne system. And basically set the frequency, acquire the data, process, get IQ, repeats for many frequencies. And with that, we set to build a transmon. The main components, the most difficult is a Jobson junctions, which is basically 2 fingers aluminum together in the tip, separated by a insulator. In that case, is a oxide, aluminum oxide. The machine that we use the technique called E-beam lithography. So we use a E-beam exposition system, which was not working so well, so we had a lot of hard work to manage to get done, but eventually we got a working junction, not perfect, but good enough for our needs. And the aluminum part, the oxide and aluminum part was done in our labs. You're using a system from Unicamp, from the Center of Nanofabrication there. Our working junction, a working sample was done in July. So here is the transmon coupled capacitively to a microwave cavity. Looking closer to it, you can see 2 junctions. Those are needed because we want to control the energy of the transmon using a magnetic flux. So here nearby, there is a flux line that we send a DC current to control the energy of the qubits. And closer yet, we see here the 2 fingers, one over another. Inside here, there is a insulator. A aluminum oxide. Not a good quality. It's a first version, but was enough for our needs at first. Of course, to set it on the dilution refrigerator and cryogenic lines, we need to have a sample holders. I designed and built those. We have 2 now, aluminum and a brass. We connected the sample to it through a wire bonder. So here's an example of the image that we did here. All those connections are necessary to maintain a good coherence. And finally, the results, what we managed to get. The first measurement and the confirmation that we had a living transmon in our sample is this one. Here is the resonance frequency of the cavity for low power and high power. For high power, there is no transmon. We saturate with the high current. It's not quantum anymore. It doesn't interact with the cavity as a quantum device. So it's practically the bare state of the cavity. But as we tune down this power, so here's the same working. There's attenuation here. We see a shift of the frequency of the cavity. That is the dressed state of the cavity. It's interacting with the transmon. So that is a characteristic curve that shows that we have a living qubits. With that, we are pretty happy with that. The next one that we wanted to check was the magnetic flux dependence. So here's the frequency, and in the middle is that same one. It's the peak of the cavity. It's the dressed state, varying with the flux. Remember the flux line that I showed you? We are saying that current, increasing the current, we see a variation of the peak that shows that we change the energy of the transmon, and therefore we change the energy of the frequency of the cavity. And the next one, we replicate a work from Schuster, where we do a spectroscopy of the qubits to see the state of the cavity, the microwave cavity. And we here show different peaks showing the occupation number of the coherent states inside the microwave cavity. Unfortunately, well, first of all, this one here shows a problem. That shows it's asymmetric junctions. So the junctions are not equal, and they need to be. We're not sure why, but we're working on that for the next version of the sample in the fabrication steps. And we couldn't get T1 and T2, the main characteristic times of the transmon needed for next steps. However, we did manage a working transmon. We have the basic techniques. We are working on improving it for the newer versions, and we expect to get, for the next samples, some good results, mainly T1, T2. And after that, we are going to join it to the non-resonators and start working on the quantum clock that we want. And that's it. Thank you for this talk. Here's the team. So here's my advisor, me, and there is also a sorry. We are working together with also people from CBPF, so Arthur and Ayara, they work together for this project. Thank you.
Okay, anyone has questions? I have one very silly, but let me walk towards Thiago for him to make a better question. But my silly one is, at some moment you said we are very proud of the pressures we get. And the not so silly question is, you can be very proud for two different reasons. To have done everything correctly and assembled everything in a good way, or to have had some good ideas of what to make better than other people. What of the two situations?
Yeah, we were proud of that pressure because it's below what of the manufacturer said it would be. So we were by ourselves, there was no technicians, it was during the pandemic. So, and then my advisor and I had to assemble the machine by ourselves and got some, we were not expecting such good results. So, yeah.
Lucas, just a quick question. So you mentioned about that graph for the coupling between the plasma, the transmon, and the cavity. Can you just go? Yeah, there you go. So, is there any effect from heating due to adding too much of RF source there? Because I would expect to see like the anti-crossing there and the other side of it.
Yeah, there's effects from heating. If you're sent to this, if you say a continuous signal, it changes a lot. Yeah, but stabilizing the dilution refrigerator, it doesn't change too much to be such significant change on the results. But there is, yes.
Okay, if no more questions, let us thank again Lucas. And we now receive Alessandro Silva Santana from the same institute to talk about quantum entanglement characterization using metamaterial circuits.
Hello, hello. Can everyone hear me?
Yes, we can hear perfectly.
So, hello everyone. My name is Alessandro. I'm also a PhD student from Institute of Physics, Klebo-Otagen. And I'm here today to present my work involving quantum entanglement characterization using metamaterial superconducting circuits. First, I would like to give a quick background of the area. The type of metamaterials that we will be using are called left-handed transmission lines, which can be implemented using a series of capacitors shooten by inductors, where each pair of capacitor inductor we call the unit cell. And as this configuration has a left-handed configuration. And this system works as a high-pass filter. And what's interesting about the system is that the density of modes diverges near the a lower frequency cutoff, which we call infrared cutoff, which corresponds to the smallest wavelength that we can have inside the systems. Né? And recently, we have shown some applications. Not we, but it has been shown some applications by using a right-handed transmission line, a regular right-handed transmission line. It is possible to realize a multi-mode strong coupling between these many modes of the metamaterial and a single qubit, which is an interesting result in CKD. If you want to, like, for example, make multi-party entanglement, study a system of many spin bosons, etc. Now, going to my project, né, which has two main objectives. The first, we want to build a system consisting of a metamaterial coupled to a mechanical resonator, né, instead of a qubit. And to do that, we're going to follow these steps. We follow these steps, né, the design of structures, design of meander, inductors, and interdigital capacitors, né, the simulation of this structure using specialized softwares like CST, Microwave Studio, fabrication, which we use photolithography, and measurement tests, where we use 1 ton, 2 ton measurement tests to characterize our samples. And the second objective, after we have our system working, where we want to put the system to test to generate and characterize quantum entanglement between multiple metamaterial modes. And to understand more how this entanglement characterization works, where we model our system, and like the system illustrated here. We'll talk about this more later. So here is our first sample, metamaterial sample that we did, which consists, we called alpha, which has 25 unit cells, and it has this capacitance inductance, which are not random, which shows these values so we can have characteristic impedance of 50 ohms for impedance matching, and also we also have a infrared cutoff close to 4 gigahertz, which is in the range of the qubits frequencies, in case you want to couple with a qubit. Here are some simulation results of the SG1 parameter, where each peak here represents one of the metamaterial modes. And here we can also see the high density of modes close to the infrared cutoff. Here I have the electric field across the metamaterial length, where I can observe a few of the standing wave patterns of the modes. So, but these were not the only metamaterials types that we use. Besides using a metamaterial with a single type of unit cell, we also try to use a metamaterial that uses 2 types of unit cells alternating between themselves, forming what we call a superlattice pattern. Né? E the only relation that these unit cells have to obey is that the ratio between the capacitance and inductance has to be the same for impedance matching. And what's interesting about this structure, as you can see in the dispersion relation, is that the spectrum is going to have 2 conducting bands. You're going to have a high-pass band right here, and we also have a narrow, smaller band right here on the lower frequency. And which can be, what's interesting about the system is that you can control the bandwidth of this lower conducting band by changing the ratio, giving you a better control for your system, for the spectrum of your system. So here are some of the designs that we made for different ratios, which of these agents has different ratios, and the respective SG1 parameters that we simulated. And here we can observe better the two conducting bands, né, of the high pass and the narrow one. So here are fabrication steps that we use for photolithography, and where we printed the circuit layout on a thin layer of niobium over a silicon substrate. Here on the side, I have a photo of our metamaterial with their wire bonds ready for our measure tests. Our experimental setup, where we have our dilution refrigerator installed at our lab. Thanks, Lucas. And we also have signal generators and network analyzers for 1 ton and 2 tons measurements. And here, I want to show a result that we did almost 1 year ago of an old metamaterial sample that we had. This is a regular metamaterial from one type of unit cell, where the results were not as expected. We couldn't observe on the SG1 measurement any modes, any peaks that we expected to see. And since then, we improved our measurement techniques and fabrication techniques. So here we have a more recent result. This one is on a superlattice metamaterial, where on this result we can observe the peaks, not only the peaks, but we can see the 2 conducting bands here. This is the first one and the second one. Here was zoom of it. And this, of course, not in our final design. We pretend to improve this systems to obtain even better results. Now, going back to the entanglement characterization. As I said before, we decided to model our systems of metamaterial using this Hamiltonian, where we have a multi-mode term representing the metamaterial modes. We have a mechanical mode and automechanical coupling, and an external drive. And this optomechanical coupling works as shifting the energy of the modes depending of the number of the photons on outer modes. For example, if I have a specific number of photons on mode 1, this mode is going to be responsible to energy shifts the rest of the modes. So it is expected for the systems to have a certain degree of entanglement, which is going to be useful for us later. So modeling the system, writing the master equation and doing some calculations, we can obtain the steady-state solution for the kth mode field amplitude given by this expression. I want to give you much details about it. I just want to highlight this term right here in yellow, which is related to entanglement between modes in the systems. And it is these terms that we're going to test and compare it with entanglement measure. So in total loss of generality, and to simplify our calculations, we made simulation for two modes. And here is the field amplitude for the first mode, and this entanglement term for this mode, where we call the X1. And here are the results that we obtain by simulating this, where we can observe a split in the field amplitude, depending of if the mode 2 has photons or not. So this blue line here shows the field amplitude in case there is no photons in the second mode, and this red line shows in case there is 1 photon in the second mode. And right here, I'm showing a plot showing this entanglement term compared with the negativity, where we can see there there is agreement between the negativity, there is agreement between the negativity and this entanglement term, which is something that we wanna analyze more deeply later. So, just to conclude my presentation, so we have designed and fabricated successfully 2 types of left-hand transmission lines, a regular one and a superlattice. And we have improved our simulations and techniques so we can obtain more experimental results. We have modeled our system, a theoretical model, and we have shown that the field amplitude has certain information about entanglement in the systems. The next steps of this project is to finish designing our mechanical resonator, which we're gonna use a piezoelectric substrate of lithium niobate, and characterize it, couple it, and finally starting working on this entanglement characterizations. And this is all I have here to show you today. Thank you, everyone. Thank you, FAPESP, for the financial support. That's it.
Questions, comments, objections?
Hi, thanks so much for the talk. So just a quick question. So you mentioned the coupling between your mechanical mode and your optics. Just the next slide.
Next.
Slide, yes. And so is GB, is the dressed optomechanical coupling or is the bare optomechanical coupling? So which means
G is bare optomechanical coupling.
So you expect to have like 6 megahertz of optomechanical coupling between your optical mode and your mechanical.
This simulation results were only to test. We test for a wide range of parameters, and but we didn't like compare with the actual experimental.
Okay.
Let me make another question in the same slide. You said that this quantity S that you are using and the negativity reasonably agrees, but for some parameters we see a double peak in S.
Yes, there is a double peak in S, right? So this means that this quantity is good to indicate if there is entanglement or not, but it doesn't work, for example, as a measurement, entanglement measure, for example. But every time the only thing we can say is that every time the models of XY is positive, the state is tangled. It doesn't give information about how much entanglement is there. It is a sufficient condition for entanglement. Okay.
And since resting on conditions like this is always disputable, do you plan to try something operational in the sense of, can we use such entanglement to do something that could not be done without entanglement, and then this is a more clear show up of the presence of entanglement?
Yeah, this is we want to study this more deeply. There is an image that I didn't put it here, but like, for example, showing that outer regions between these two splits, its entanglement using S. I'm sorry, it's not here, but yeah, well, I found it interesting. But we plan to look this more deeply and see if we get some interesting results.
Okay, any more questions? So let's thank again Alessandro. And now let's go deeper, since it was introduced as a PhD and postdoc session, but we have a master's student also presenting his work. So please, Arthur.
Perfect. Hello. I am Arthur. I'm presenting a work I'm doing in my master's under the supervisory of Professor Marcelo. And this work was done also in collaboration with Dr. Roberto Baldigion. We're essentially investigating what happens to state-independent contextuality when it's subjected to a multiple observer setup. So let's think a little bit about that. So we're talking about here coherence patterns contextuality, and this is something that can also be defined in a couple of ways, but what is mainly interested to us here is that it is a property of quantum systems where the outcomes of the measurements cannot be thought of as revealing pre-existing values. And the way we try to measure if we have contextuality in a system is through violations of non-contextuality inequalities. So depending on the system, we have inequalities that basically establish bounds that must be respected by any non-contextual statistics. So in practice, what we can do is that we have finite observers with finite outcomes. We can see what happens if we exhaust all the possible outcomes of these observables with deterministic outcomes. And this gives us a bound that any non-contextual statistics will need to obey. And if we test this inequality and we find a violation, this will be showing us contextual behavior. So in a sense, we are studying if the randomness that we see is fruit of, in a sense, hidden variables, like, for example, in a deck of cards that we can scramble, and the randomness there exists, but there is a deterministic outcome in the top card here. So this would be non-contextual phenomenon. So, like I said, to test contextuality, we need to see if we can find a violation of the inequality. So this inequality will be an inequality of the statistics of our contexts. So to test them, we generally have a single observer, say Alice, and she has a couple of contexts that she needs to test and find the average value of them. And the way she does that is that she takes one context at a time and does a few measurements rounds. So a state row 0 is prepared. She has, for example, now to test context ABC. She does the three measurements in sequence, gets the results, then throws out the output state here and starts over. So we basically have many of these rounds. What I'm calling a round is after she finishes to measure a whole context of the compatible observers here. And we can see that these equations, these inequalities, can show us two types of contextuality. So if we see this, if we have a violation, regardless of the state row 0 that is prepared here, so we're thinking that every round we prepare the same row 0, and if for any choice of row 0 we find a violation, then we have state-independent contextuality. If only some row 0s reveals to us violations, then that is state-dependent contextuality. So that's the main difference we'll be looking at here. The starting point of this project is when we think about what happens if we introduce other observers to this game, right? So this is a paper that started with Professor Terral Cunha and Roberto Baldigion, investigating if we can still violate these inequalities when we have multiple independent observers doing a similar protocol. So, for example, here we have Alice trying to get statistics for the context ABC, and Bob is trying to get statistics for the context DEF. So Alice is gonna behave as normal. She's gonna take the state rho0. She's gonna go, oh, I'm first gonna do measurement A, then B, then C. And we say that it's independent observers because she really doesn't know what Bob is doing here. So Alice just goes on as normal, does measurement A, gets result OA, and it takes a little while to do the second measurement. And in this in-between moment, Bob does his first measurement D in the output state of Alice. So Alice is now going to do her second measurement in the post-measurement state of Bob. She really doesn't know what he's done or what he's doing. She thinks she's in the first situation that you showed. And this back and forth happens a couple of times. So Alice is going to do her A, B, C. Bob is going to do his D, E, F. But they take turns accessing this system. And we want to see what effect this has on their ability to violate their inequalities with their statistics. So the situation that they were examining in their paper, Marcelo and Roberto, were different inequalities in different multiples observer setups, so we can alter some of the conditions if they have, for example, a fixed order to access the system, so a couple of parameters. But one of the examples is the Cassibiès pentagram inequality, that we have 5 observables that are pairwise compatible, so each adjacent observable is compatible, so here 0, 1, 1, 2, 3, 4, and it has this inequality here for the average values of all these contexts. Of course, this is a known state-dependent contextuality, so this inequality can only be violated if you test it with some specific states. And what they found is that even when you use these states that violate the inequality, when you start to add more observers, there is a maximum number of observers that can violate this inequality. So if you add a second, a third, a fourth multiple observers in that protocol, they can still witness a violation, but at a certain point, further observers cannot find violations anymore. So this is at first not exactly very surprising if you think about it, because if this inequality is very sensitive to the state you use to test it, and that state is rho0, after Alice does her first measurement, now Bob is not measuring anymore in state rho0. And if only some states can violate this inequality, you might say, well, the more observers we put here in the setup, the more degraded the state gets, and it comes to a point where we can no longer see violations. And well, if that was all that was happening, if we used a state-independent inequality, we would not see this same phenomenon. We could add as many observers as we want, and they would all be able to witness contextuality. So that's the starting point of our work, is to test this with a state-independent inequality. What we used is the Peretz-Mermin square, a 2-qubit system with these 9 observables that we can basically display on a square. And the context, the maximum compatible observables, are the columns and rows of these squares. So any column will be a context, and any row will be a context as well. And the output of the measurements is -+1. we have here a state-independent inequality, a non-contextuality inequality right here that has a classical quota of 4. So any non-contextual value assignments to these 9 observables will yield a value of sigma here that must be smaller than 4. But if we look at quantum mechanics, it shows us that whenever we multiply any row or column, here most columns we get the identity, and this last column here we have the multiplication of it is minus identity. So when we get the expected value of this, since we have minus here and we have this minus sign here, it's just 6 times the expected value of the identity, which is equal to 6, independently of the state used to measure here. So this is a state-independent contextuality, because any state we use to test this will give the maximum violation of 6, well above the 4 classical quota. We created a setup, what we call the public system setup, where we have a main observer, that's, we say Alice, that's trying to see a violation. So she's measuring 1 context per round, and we have many other passerby observers that are basically randomly measuring from the Peres-Mermin square. So they are not really trying to measure a context or see violations. They're just randomly measuring here in their turn one of the measurements from the square. And what we actually see is that when we simulated this computationally, of course, when we have 0 passerby's observer, as we expected, Alice will get here the maximum violation. But as soon as we add another observer here doing the measurements in between, we dip the value of sigma Alice gets dips below the classical, the quota we have here of 4, so we don't see contextuality anymore. So this is the main result that we get, and I'll probably get here to the conclusion, is that state-independent contextuality can also not survive this multiple observers setup, and this tells us what does it mean to actually, for this contextuality to actually be independent of state. It doesn't mean that we can do whatever we want to the state in between these measurements. So it's independent of the state used for the measurements, but it has to be the same state within all the measurements of a context. It's quite sensitive to what happens in between the contexts. And this also shows us that noise, that if you were to implement this experimentally, even with state-independent inequalities, you have to be very careful about the noise in between these measurements. And this is one of the factors that also may inhibit experimentalists to getting the predicted quantum quota, not just the, for example, problems with the measurements and implementing measurements. The noise itself can also be a problem. This is mainly it. Thank you very much for your time.
So, Marcelo França will make a question.
Thanks for the talk. So, I have actually a twofold question here. So, the first question is, Bob is being radical in what he's doing, in the sense that he's making a strong measurement. Have you guys thought about checking like a measurement that is almost doing nothing but doing a little bit of a measurement? So what I mean is that you change only a little bit the state, not radically change the state. Mm-hmm. So that's the first question. Then the second question is, how do I connect this, what I have just said, with the possibility of having kind of non-Markovian behavior between what Bob is doing, in the sense that what he has done what he's going to do in the second step is not independent of what he has done in the first step. So I kind of have the feeling that you could recover the violation in some of these scenarios.
Okay, this is a very interesting question. So at first, we're very interested in trying to get less, like I said, radical interferences from Bob, because it would be quite interesting and useful if the first or the second additional observers didn't entirely destroy contextuality, if just the fourth or the fifth, so you could maintain it a little bit. So we have tried a couple of things, but so far we have not been quite successful in it. And about the Markovian behavior, the first thing we tested that was non-Markovian was, well, what if Bob is also trying to violate the inequality? So his measurements are not exactly independent because they have to be inside the same context. So that is basically the only non-Markovian thing we try to implement. And the reason is that we also wanted to model this as a quantum channel. So being a Markovian behavior made it more simple. So we really didn't focus very much on the alternative.
And in the end, you came back to the answer of the first question.
Yeah.
Instead of measuring, it's just a channel. It is something less radical than a measurement.
Yes, yes.
Any more questions? So let us thank all the speakers of this in-between session. So now we have a coffee break there, some tests
am I all set? Can I start?
Yes.
Yes? Is there a pointer? This one? Okay. So, probably as in a movie, good morning, good evening, and good night, given that people are most likely all around the world. It's a pleasure to be here. I would like to thank the organizers for putting together this session so that we can talk to you a little bit about our efforts at developing quantum technologies in Brazil and Latin America. Is there no sound? Aha.
So you can start again, please.
So I will start again. Now, apologies for those who weren't listening. Again, good morning, good evening, and good night, anywhere you are on the planet, and maybe there are people even in the International Space Station watching this, so even off-planet. It's a pleasure to be here. I would like to thank the organizers for putting together this session so that we could talk to you about quantum technologies that we aim to develop in São Paulo, Brazil, and Latin America. Just so you know, there's a local initiative. These people are responsible for it. I will talk to you a little bit more about that, about a workshop that was organized from January 30th to February 16th this year. Now, what is all this about? Okay, no battery. So, sorry for that. What is all this about? Uh-oh. I guess that's not the problem. Okay, now it is working. Maybe this was working. Okay, so we're all facing a new quantum revolution. Obviously, if I'm talking to you all over the world and using all these equipments, it's because there was a first quantum revolution in which we were able to unravel the details of the structure of matter, properties of atoms, how atoms interact. We're able to put together all sorts of solid-state systems, and we use these solid-state systems to process, to store, and to communicate information quite efficiently. Yet, there's more to quantum mechanics than what we've been using so far. And you've certainly heard there's a next quantum revolution coming around. What are the main ingredients of this quantum revolution? I would pin them down to interference and indistinguishability, to incompatible measurements, thus uncertainty relations, and quantum correlations and entanglement that entail from these principles. Quantum correlations and entanglement enable us to think fundamentally differently about the way we process information, about the way we store information, about the way we convey information. And this is what this new revolution is all about. This second wave holds promise that a lot of you must have heard about quantum computing. So the fundamental unit of information processing being a generalization of the fundamental unit of information processing that we have in our regular computers. Bit will become a quantum bit, and that opens up all sorts of possibilities. There are many companies around the world working. This is just one example of a quantum computer being developed at IBM, but there are others in order to process information more efficiently and enable us to deal with certain problems that are intractable with current day technology. There's promise for quantum communications, both in terms of more efficiently conveying information and in terms of securely conveying information, basing the security of information communications not merely on some mathematical complexity, but on fundamental properties of nature. And then quantum sensing, which I will talk a little bit more about in this talk. And obviously, a promise that from very fundamental quantum science, we can have significant economic consequences. So there's an estimate that global markets for various quantum technologies will be above $1 trillion, led by photonics, semiconductors, and cybersecurity. So why do we need a national quantum initiative in Brazil? Well, at conferences like this, well, not exactly like this, the conferences, the usual conferences in the pre-pandemic era in which we all met in person at locations around the world, many of us were approached, many of us, I mean, from the scientific communities in Brazil, Chile, Argentina, other Latin American countries, we were approached by people asking, since you have such a strong footprint in quantum information science, how come Brazil is not a major player in quantum technology initiatives? How come there is no national quantum initiative in these countries? So there's this company, QuReqa, which mapped efforts around the world. I'm not going to go into the detail of all these efforts, but just to say there's an estimate of a $33 billion effort globally in 2023. Before 2023, in their previous update, this area was entirely gray. Now Brazil shows up on this map with an effort of 60 million real, $12 million, and that is actually a gross underestimate of what's going on in Brazil. This is just one initiative by a company called Embrapi, which launched a call for proposals. There's a lot of other efforts in terms of quantum information science that should go in this picture. But still, it's a modest effort compared to what we represent in the world and compared to the quality of the science that we have here in Brazil. Now, we want to fill in this picture to put a number that would be more representative of what our scientific community means in the world. Through the pandemic, so right before the pandemic shut everything down, we were approached at conferences. It took us 6 months to get together in the state of São Paulo. I am definitely not going to dwell on the Brazilian politics of the time. Didn't seem very likely that we would be able to have a federal initiative, but it was definitely likely that we could have something going on in the state of São Paulo, where we have a very strong funding agency for science, FAPESP. So a bunch of us got together, August 17th, 2020, had a first Zoom meeting, and then a whole series of events. We've been working together hand in hand. We've been getting a community to join efforts to propose first an initiative for the state of São Paulo, but obviously from the very beginning, given that our scientific community in Brazil and in Latin America is closely collaborating and has been closely collaborating for at least the last 20 years. We will hear more about it from the current coordinator of the Brazilian National Institute for Science and Technology and Quantum Information. We've been working together, and so obviously from the beginning our aim was to have something that would happen at the national level and obviously also extend to a regional level. So this is just to give you a timeline, and this ended up, or resulted in a 3-week workshop that was carried in late January, early February this year, with the purpose of writing a quantum technologies roadmap for Sao Paulo, for Brazil, and for Latin America. So, yeah, this is a little bit slow. And I think, unfortunately, it's my computer. And this is ridiculous because my computer is, it's a classical computer, but it's not an old one. Okay, there. So these are the people responsible for these initial efforts. I want to point out Professor Marcelo Terra Cunha, who is the organizer of this session. And just to give you an idea that, there are many people from the University of São Paulo, but we have people from Unicamp, from the Federal University of São Carlos, and we've been gathering support from many more people throughout the state and throughout the country. How do we do something like this? 4 main, ideas. We need to have focus, build on our strengths. We need to work to build capabilities, to use the kind of capabilities that we have. We need both innovation capabilities and we need entrepreneurial capabilities, and this is a challenge for us in the near future. Collaboration is key. Collaboration between academia and between the private sector, collaboration between our different institutions, our different research groups, our different states, our different countries. And readiness. And readiness is obviously also, very important in this whole effort to educate a quantum workforce. This is a challenge that is going on worldwide. It wouldn't be different in Brazil. In Brazil, we are focusing on attaining that kind of readiness by educating engineers in quantum science. Now, I think this is an important, wake-up call for many of these countries, such as ours, that understand the need to develop quantum technologies, but for which it would be foolish to compete to build quantum hardware for quantum computing and try to compete with the big players, the big companies that are involved in this game at this stage. So can we profit from quantum technology without building quantum computers? And the answer is obviously yes. There's a lot of potential market, not only in supporting value chain, but also on different niches in terms of the quantum technologies. When we talk about quantum technologies, it's natural to think right away of quantum computing, but quantum computing is not the only quantum technology that has a lot of promise for the near future. So do we have the capabilities? Do we have critical mass in Brazil for this? This is a picture, a little bit of the distribution of research groups that, so in the academic setting that develop quantum information science in general. I'm sorry, my son doesn't know that I'm giving a talk, and so he's calling me on the phone, and my watch vibrates, so it's disturbing. So these are just a few of the words that show the kinds of activities that are going on in the different regions of Brazil. We have a strong presence, obviously, in the southeast of Brazil. We have strong presence and tradition in the northeast of Brazil. We have groups in the southern region of Brazil, and we have some groups in the center-west of Brazil as well. As I mentioned, there's a National Institute for Science and Technology and Quantum Information Science, led by Professor Belita Koiler, who will be our next speaker. And again, we have about 120 faculty in universities throughout the country that are involved in this effort. We've been doing pretty good science. We've been working on many different aspects of quantum information science. Just to give you, a little flavor, continuous variable entanglement, contextuality, which we will hear a little bit about maybe later in this session, non-locality, photon correlations, quantum thermodynamics, optomechanics, synchronization of oscillators, quantum teleportation, optical vortices. There's a strong academic community in many different fields involving different possible technologies that can be developed. Now, one of the reasons why it's so challenging to build quantum computers is because quantum systems are fragile. They interact very, very strongly with the environment. Now, what is a difficulty in terms of building quantum computers is actually, a message that quantum systems interact very, very strongly. They're extremely sensitive to the environment. And so, as Sir Peter Knight says, we can turn it on its head, right, and use these quantum systems for exquisite sensing. This is a great potential for us here in Brazil. So just to give you an example of, as I said, key ingredients: indistinguishability, interference. So for instance, one can use interference between atoms to actually take quantum sensors from the lab to real world applications. This is a review in Nature Reviews Physics, December 2019. And I would like to point out that two authors in this review, Philippe Bouillet and Wolfgang Schleich, and actually we had also contacted Kai Bongs, are participants in our international committee to help us, build this effort for our roadmap for quantum technologies. So I won't dwell on this, just to show that an atom interferometer can give us exquisite sensitivity to measure gravitational fields, and that means that we can build gravimeters. Professor Philippe Courtet and Professor Romain Bachelard in São Carlos have been using these kinds of principles to develop gravimeters. They hold a patent on that, and with these gravimeters, we can learn about things that are buried underground and have information that will help us either know what our resources are or know when we want to build something, whether we're going to find rock or whether we will be able to dig further down. So the workshop that we held for 3 weeks had 51 attendees from 8 countries, 9 different Brazilian states, and this is just to show you that there was a lot of activity during these 3 weeks. We had the presence of different authorities, the former Minister for Science and Technology and Innovation in Brazil, Professor Sérgio Rezende, who was extremely supportive of our efforts. Our international committee, as I said, Professor Stephen Walborn from Chile, Professor Juan Pablo Paz from Buenos Aires, who will speak later in the session, Philippe Bouillet, Wolfgang Schleich, Cristiane Moraes, Heiner Blatt, Professor Luiz Davidovich, great inspiration and leader in the field in Brazil, Fernando Brandão, a Brazilian pride at Caltech and Amazon, Arthur Eckert, and Simon Grobelacher. And Arthur Eckert actually said something that is very important when we were discussing with Brazilian authorities. We are preparing a roadmap. Now it's time to build the road. So we need, to join these efforts in order to go from roadmap to road. Okay, just a background again. University of São Paulo and São Carlos. We are getting together with Embrapa Instrumentação. There will be a workshop on this on Friday to talk about quantum technologies applied to agriculture. And different universities, São Paulo, Federal University in ABC, Unicamp, Federal University of São Carlos, and companies that are also already joining and building this ecosystem. I don't want to dwell too much on the potential markets. There's possibilities for the food chain, for finance, for energy, for defense, communications, health, you name it. This is a little bit about the weeks that we took in our workshop, the subjects, mapping quantum initiatives around the world, the readiness in our country, in our state and our country, sensing, communication, computing, agriculture, health, quantum education and dissemination, the role of our funding agencies and companies in order to take this roadmap further. I want to say something about, one of the important things in our initiative, in our roadmap, is to look at opportunities where we can be unique. What kind of promise do we have in this country that will make us major players, not just people who are, not being drowned by the quantum wave that is coming, but actually major players. And one of them is agriculture. So we found out that in other places, people are already using quantum technologies in terms of developing sensors to improve farming. Now, there are reports from the Food and Agriculture Organization of the United Nations that indicate that food production will have to increase by 50% from now until 2050 in order to feed mankind, so humanity. Of this effort, if we look at what role Brazil should play, this is from a FAO report, and we can see that places where food production has to increase a lot, Brazil and the whole of Latin America plays a very important role. Now, this report from PwC says Brazil could, with the potential we have in a scenario of a climate crisis, respond for 40% of the additional food demand expected for 2050. What that means is science for increasing food production and agriculture has to be developed mostly in Brazil. We have to be the center of the world in the development of science for this. And the next wave is quantum, so we better get started building quantum technologies for agriculture. These are just a few examples. Quantum dot labeled immunoassay to determine pesticide residues, agricultural gas flux determined by dual comb spectroscopy. Actually, this is a paper with one of the authors is Brazilian. This was done in the United States. Remotely piloted aircraft system to do detection via spectroscopy. At Embrapa, we will hear Embrapa Instrumentação, a group that is developing laser technologies in order to measure plant properties by what's called laser-induced breakdown spectroscopy. So these are the challenges. I've mentioned a few of them. Really educate a quantum engineering workforce, engage more engineers, but also chemists, computer scientists, mathematicians. Think about multi-user facilities, test beds to advance hardware development, enhance the interaction between companies and our research institutions, create a culture of innovation, entrepreneurship that will lead to a strong ecosystem, and obviously be able to cross the death valleys that always exist between good ideas and commercial products. So I'm not going to go into much detail because this is very Brazilian-centered, but we are very hopeful that the funding agency in São Paulo will adopt our idea to create a program on quantum technologies. Our science ministry and other state funding agencies are also interested in working together to develop a strong national quantum initiative. We expect to have strong involvement from the federal government. And as I said, this is not only a science, technology, and innovation effort. This deals with health, industry, agriculture, communications, education, defense, foreign affairs. So this will have impact on all of our society. I should probably stop here. I would just say that it's also fun. So whenever, if you want to come to in-person events in São Paulo, I'm sure the International Committee will agree that we know some very good restaurants here, very good local food and local beverage. So thank you for your attention.
Thank you very, very much, Paulo, including for making the talk in the schedule. So please, who wants to make questions? Remember to introduce yourself before making the question.
Thank you. So I am Roberto Baldijão. I'm now working at University of São Paulo. So Paulo, thank you very much for the talk. Well, as physicists, we know that sometimes it's difficult to speak and collaborate with people from slightly different areas, right? If you're a theoretician or an experimentalist, maybe it's very difficult to find like the way of creating the language where both can speak and understand each other. So my question is, how does the initiative hopes to make such different fields, such as quantum physicists, mathematicians, and engineers talk to, for instance, enterprises that deal with farming in Brazil and stuff like that?
So thank you for the question. It's a very good question. The answer is effort, right? We have to put a lot of effort into it. We have to be very careful about jargon. We have to present them with the basic ideas. So what's different? What will make these technologies successful? And we have to listen a lot. So this is a kind of situation in which, as physicists, we know that we have exquisite sensitivity to measure all sorts of physical properties of different systems. We can do it through electric fields, magnetic fields, with optics, with plasmonics, with whatever, right? So we can measure things with exquisite ability, and we've been working a lot on packaging things smaller and smaller and smaller with the interaction with engineers. We need to talk to people that are into plant sciences. We need to talk to people that are into soil analysis. We need to talk to people to understand what are the properties that we have to measure, what are the limits in sensitivity. So the answer is effort, and this is why we have started talking with people, for instance, from Embrapa Instrumentação. I've been visiting the agriculture school at the University of São Paulo in Piracicaba, which is extremely strong in terms of all sorts of plant sciences, mostly from the biological point of view, but they've been, they have a growing interest in this conversation, right? So the workshop on Friday, for instance, is one opportunity for us to tell them a little bit about quantum science and to also visit different laboratories that they have and learn about, what's important to measure, how can we do it? So talk, 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 listen, listen, listen.
While I wait for another hand, let me include in this answer that as this event of Embrapa is happening this week, probably next month, also this week, there is a discussion of an event that probably will happen next month at SEMP in Rio de Janeiro to discuss perspectives for the oil and gas sector. And again, we need to be there discussing, listening, speaking, talking. Any more questions? Not for the moment. Okay, so thank you very, very much, Paulo. And let us move for the next speaker, who will tell us a little bit, because the time is short, about the history of investments that we have in Brazil. So now it's time to Here she is. Very good, Belita. So you can start saying some words if you want, but then you share your screen with the green button and then go on. So Belita is our coordinator. Sorry, Belita, I should have introduced it before. So Belita is our coordinator of the National Institute of Science and Technology in Quantum Information, and she works at Federal University of Rio de Janeiro, and she will now give us this talk here.
Can you see my slide?
Yes, perfectly. Probably you need to enter in the presentation mode, because we can see it as if you were preparing it yet.
Where is the presentation mode?
Play thing.
Okay.
Yes. And let us hope it works. Yes, perfectly.
You see both me? Well, I'd like to make this thing at the right smaller.
It's very good. We see you in a small window and the presentation in a big one.
You still see me because I don't see me?
Yes, yes. Okay. Sorry, you do not see us, but believe we are here listening to you.
Okay, okay. So thank you very much for the opportunity to talk about our institute. I think I'm going to complement Paulo's talk because he's talking about the future, about the roads to go on, and I'm going to talk about the past, how Brazil reached the current position in quantum information and quantum technologies. It's a complement of what Paulo said, and I thank these people for helping me with the slides. So I'll start by, wow. Okay. There's a program run by the Brazilian Minister of Science and Technology and by CNPq. It's called the INCT, Institutos Nacionais de Ciência e Tecnologia. These are actually virtual institutes, are networks of scientists with common research interests in all areas of science, but in particular, in physics, we have this one of the institutes which were selected by an international jury that recommended a few, around 100 institutes, and we were one of the indicated. But you see, there was no, I don't know that we have a roadmap. It's free. Any research on quantum information is welcome, and basic science is predominant. So I'll talk a bit about the history. The idea of virtual institutes or networks started with the program called Millennium Institutes from 2001. And the first edition, it had 2 editions. The first edition from 2001 was coordinated by Luis Davidovich and got an amount of money that was to be decided by the committee.
Belita, sorry to interrupt you, but we are still in the first slide. Are you changing slides or not?
Yeah.
So
yeah, I'm changing.
Please, sorry for that. You have to unshare the screen and then share again the screen of the presentation, not of the program that we're using. Yes, at Zoom, you have to unshare the screen, or I can try to do it.
Stop video? Well, at what? I don't know. I don't know how to do it.
Never mind, I'll do it from here. But
okay,
now, when you share, you have to share the one that's the presentation in the presentation mode. And not,
okay.
So try again.
Okay.
This is a bug from the presenting stuff.
Yeah, I learned a lot of bugs preparing this talk. I learned many bugs of the computers.
Yes, you can write about the bugs of the presentations.
Yeah. Okay, so what do I do now? Do you see something?
No, not yet. Now you have to
go to the
presentation. Green share screen button, And then
Oh,
share.
Green. Share screen.
Yes, and then choose the one that is in the slide that you were showing to us.
Okay, this one, I guess. Okay, is this it?
This is the program, but
Oh,
okay.
yeah, this.
You can try to follow
Then
this.
I go to play.
But then move from slide to slide by yourself, because we are seeing the first one, the one with the cat.
Okay. So, can you see the screen?
We see the screen, but we see only the first slide. So
Still?
still, yes.
Oh. Oh, I'm sorry. I don't know where to go. You are screen sharing. I stopped screen sharing, right?
Okay, we will
Yes,
use the slides that you have sent to us, and then
Okay.
it will
Because this is very confusing.
probably. This is why we had the plan B, so let us use it. Sorry for that.
So then I have to tell you when to change. Can I change?
No, never mind. You only need to talk. We will share from here the slides that you sent to us. But we
Okay.
are still opening it.
Sorry.
So probably you were.
Okay, I was already. I tell you when to turn or I can turn. I cannot turn.
Yes,
Okay.
probably you were
So,
here.
Yeah. So the first national program of networks in science was called Institutes of Millennium Institutes. And our group started with a first Millennium Institute coordinated by Luis Davidovich. We cannot say enough about Luis. He is really the attractor and the inspiration for everyone in the institute. And so he got an amount of money at that time, 5 million reais. And then there was a second edition of the same Institute of Millennium in 2006. And then the coordinator was Amir Caldeira, who's a brilliant theorist and from Unicamp. And then he got $2 million reais. And then they started a new program. That's the one we are running now. It's the National Institutes for Science and Technology. And there was a first edition where it still was coordinated in Campinas by Amir Caldeira. And he got 8 million reais. And then there's a second edition of this same program that started in 2014. And we got 10 million reais. You cannot compare the numbers because the inflation in Brazil is, well, you change the, don't move, okay. And then I'm going to say a little bit what happened in each of these stages. See, it's about 5 years each program. And now next slide, I'm going to describe what happened in so Millennium 1, it started building infrastructure and with experimental priority. So there was basic infrastructure for theory research, but the experimental activities were given priority. And an important event that happened during this Millennium 1 was hosting the PASI, Pan American Advanced Studies Program of NSF, of quantum information in Brazil, co-funded by the Millennium Institute. So it's a joint NSF Millennium Institute initiative. And this was a milestone for the international insertion of our activities. And already some important papers were published at this time, physical review letters. And the use or the benefits from the infrastructure with all the state-of-the-art equipment that was arranged in Millennium 1 was profited in Millennium 2 in 2006. So made good use of the new infrastructure. And there was a lot of progress on the ongoing work. And previous results were improved in quality and quantity. And then we started publishing in journals like Nature and Science, and joining many experts in physics, chemistry, mathematics, and computation. Next slide. So now we go to the EINCT first edition in 2009. And there was a big expansion. The number of researchers participating in the network raised to more than 70, many graduate students, postdoc, 20 research groups, 12 laboratories, 15 institutions in the states of Rio de Janeiro, São Paulo, Minas, Pernambuco, etc. And the project, again, it was given priority to the experimental activities. And in 2014, Brazil joined the World Map of Quanta. It was raised to rank among the 20 top countries in the field. I don't know who did this research. I found this in an old slide, but it was ranked to be in the top 20 countries in the field of quantum information. And then we go to 2014, the second edition of ENCT, and this is the one I coordinate, and Luis Davidovich is my deputy coordinator. But we are going to see where next slide we see where the groups are located, and this is very similar to what Paulo showed. Can you go to move to the next slide, please? Okay. So this is the regional distribution. A little bit, it's very small. I don't think you can read, but it's the same area, same group, same geography that Paulo showed for the activities he was presenting. So 28 institutions, the same number, it's funny, it's the same number as Paulo showed in his roadmap. It's just 120, over 1,000 published articles. And the current edition has 120 dissertations and 168 theses in preparation, plus the 200 graduate students. So it's a big network with all fields. I'm going to talk about the field. The labs, the experimental facilities that were mainly bought with the money from these networks is listed here. Institutions from Rio, Goiás, Pernambuco, Alagoas, Fluminense, USP, São Paulo, Rio de Janeiro, Minas Gerais, many parts of Brazil, as I showed before. So these are just the experimental facilities. Next slide, please. Next slide. Okay, so this is something Paulo already mentioned. I'm going to repeat. Quantum concerns are all of us. Why is that? The first warning came from Moore's law that showed that the number of transistors in a chip doubles every 18 months. So if you go to the number that will reach in a few years, maybe already now, you go to a chip that will have only one or a few atoms. And of course, the physics is different at this scale. You go to the quantum world and living the transistor world, if you want to say. So the first one is there, but then we are now at a stage that more concerns are in attention. So I changed the slide again. Slide, okay. So beyond Moore's law, we have in 2023, quantum information in the center. The input is quantum physics, theory of computation, theory of information. And now the output is going not only to quantum computation, but quantum communication, quantum cryptography, quantum metrology, and quantum thermodynamics. And then next slide. What's being studied in the institute? the same new fields. So there is activity in all these new areas of quantum physics. And I cannot show you all the works. There are important contributions in quantum computation, communication, cryptography, metrology, and thermodynamics. But I'm sorry I cannot explain everything to you. So I'll just go back to current computers. They are binary. And transistors are the active elements in the chips. And so in a quantum computer, you don't have bits, you have qubits. And a qubit can be defined as any two-level quantum system as illustrated under and below. So the idea is to explore quantum phenomena such as superposition and entanglement to perform operations, and they differ from traditional computers that are based on transistors. The basic principle behind quantum computation is that quantum properties can be used to represent data and perform operations at this data. So this is well known. And we need to define qubits. And I'll show you many options of qubits that are developed in our institute. So they can be photons. Next slide. Qubits can be atoms, and atomic physics is also in our labs. Next slide. Ions and nuclear spins. This is an accelerator that a Van de Graaff type. Magnetic flux in superconductors. This is also work being developed in Rio, in CBPF. And this is a theoretical work, but it's being studied spin in semiconductors. So this is not in our labs. And I'll just give you an example of a fruitful diffusion of AIMCT elements. Just an example, it is my work because I wouldn't be able to talk about other people's work, but it was a collaboration between Rio researchers and Minas Gerais researchers. And it was chosen as editor's choice in Physical Review Letters in 2017. And it's called Photonic Counterparts of Cooper Pairs. We speculated, also later, I speculated that photons in a laser, in the material, would show the same pairing behavior as electrons forming Cooper pairs in superconductors. And this had a tremendous impact in all, in the press. We had lots of reviews, and I'll show you. So in Nature we have here, and the co-authors are Aldo Jório from Belo Horizonte, who's experimentalist, Carlos Monken, André Saraiva, me, and Marcelo, paleólogo, who's there with you. So photons couple like Cooper pairs when light attracts light. And so I'll show you what can be. Next slide shows more about this work. This is a news article in Nature about our work. And so I explicitly say that in this table I show photon pairs is a subject of quantum optics, and electron pairs, Cooper pairs, is a subject, is superconductivity. The photons pairs were studied experimentally by Raman scattering by Aldo Jório, and electron pairs were studied theoretically by the condensed matter theory group. The coupling mechanism in photons, speculating, is that a photon emits a phonon because it's a material medium, which is absorbed by another photon. This would be a Raman process. And the coupling mechanism in Cooper pairs is an electron emits a phonon absorbed by another electron. So the photons would interact via exchange of phonon, and the electrons also interact via exchange of virtual phonons. So Raman scattering coupled to quantum optics gave a very impacted result. The phenomenon, the consequences of this phenomenon, or if it really exists, is still being investigated theoretically, mainly by Marcelo Paleolo. But this was an analogy that caused a lot of impact and interest in the world's literature. And so the other contributions are in our site. And so it's listed in the left column, the entity for divulgation. And other strong actions are technological activities. There are some groups that collaborate with industry. There are popular science activities on quantum information that are presented to schools and young people. And there are special activities for public schools, for girls only. I should mention another thing that are yearly meetings of the institute in Paraty. And so to finish, I'm going to talk about this Aldo Zorio again. He to do the Raman experiments on the photon pairs, he developed instrumentation for this purpose. And here's another example of his quality. And he was at the cover of Nature, where he developed an instrument that is able to rotate a graphene sheet over another. So thank you for your attention. I'm sorry if I was too long, but that's it. I think that's it.
We are sorry for the technical problems, Belita. Any quick questions?
Okay, I hope
before we move to Aldo? Not. So please, Aldo, and let's thank again Belita.
Thank you. Thank you for the opportunity.
I'll need some help to find your presentation. The first one. Okay, perfect. So here we are, and then we have to come back to Zoom. Ops, perdão. Vai. Deixa eu pegar minhas. Sorry. Take this. Do I need to use the headset? Yes, I think. No, I think you can use.
Okay. Bien.
This is for you. This is for me.
Okay, and this one is to change the slide? Yeah. Okay.
So, Aldo Delgado from Universidad de Concepción and the director of MIRO, the Millennium Institute for Research and Optics in Chile, who kindly came here to give us his talk. Please, Aldo.
Okay, hi everybody. It's a great pleasure to be here again in Brazil once again, and thank you very much for the invitation to present this talk here. As Marcelo was telling you, I am going to introduce the Millennium Institute for Research in Optics, which I am the head of. This research institute is dedicated to the study of light and its interaction with matter, and to study any feasible application of light and its interaction. The institute performs mostly experimental research in 5 different universities. Each university contributes to the institute with an experimental facility. From the legal point of view, we are a corporation, non-profit corporation. We have a board of directors. I am the head of the board, which means that if something goes horribly wrong, I am the one who goes into jail. So I am the most interested part that nothing goes horribly wrong, you know? Then we have the associate researchers, which are members of the board of partners. We have an executive director, legal accessory, because I don't want to go into jail, you know, management and budget. communication and outreach, and then an accountant and press support. Our budget is about $1 million per year for 10 researchers in these 5 universities. We have 4 main research lines: optical communications, photonic lattices and path information, quantum light, and novel light sources. Now, optical communication is trying to do the following. They want to encode information in light and transmit this light across free space. What light do they choose? They use light with optical angular momentum, because in principle, this type of light is more robust against turbulence in the atmosphere. They have been able to generate a state of light with orbital angular momentum inside the laboratory. They have reached around L equal to 50. In distances, first about 4 to 5 meters, then they went to 80 meters, and now they are doing this in about 800 meters in free space. And the next stage is that we expect to reach 3 kilometers inside Santiago, okay? And the next level will be to do this using quantum light, because this is classical light, okay? The main problem that we find in this type of setup is attenuation. We lose a lot of photons because the atmosphere in Santiago is not very transparent. You know, there is a lot of smog. We have also been wandering, so the light start to move and never reach the detectors. And then we have the problem that you have to detect efficiently the information that you are encoding in the light. And for that, we have the problem of crosstalk. If you encode a given value of m angular value, then you get a superposition of several m values. Okay, so you have crosstalk. Then the next research line is photonic lattices and path information. This laboratory is mainly dedicated to study complex systems. They do the following. They use a spatial light modulator, which generates a beam of light which has some topological charge. Then they illuminate a liquid crystal light valve. The liquid crystal interacts with this topological charge and creates a topological charge, but inside the matter. So you can map the vortex, the optical vortex, into the matter. And then using the light valve, you can change the properties of the liquid crystal, so the process becomes non-linear and terribly, very, very, very complicated. And that leads to the generation of very interesting patterns. The second setup they have is the femtosecond laser waveguide writing. So using this facility, they can create almost any array of waveguides inside the slide, porta objeto. Okay, we are doing this from 2 years ago. They have published a large number of papers, and now they are working on what they call splitters. So by adjusting the length of the waveguides and the coupling constant between the waveguides, you can shine light on only one of them and then split the light across several waveguides. That's what they call splitters. And you can use these to implement logic on optical state of classical light. So you can calculate with this stuff. And they have also found that they can create what they call an optical key. They can encode information of a key inside the structure of these waveguide arrays in such a way that you get a key. This key has been proven to be very secure, and it has been patented in the United States. We are about to launch start a company to see if somebody wants to buy this stuff, and we get rich in the process. Because, you know, that's the motto. Go quantum, get rich. And then we have quantum light. So a few years ago, we started with a very simple experimental setup, at least conceptually. The idea was that we use a source of light and 4 concatenated spatial light modulators. The first 2 light modulators were used to encode a high-dimensional quantum state in a single photon. The last 2 modulators were used to project this state onto any other state. So this was like a higher dimensional version of the Bohr's rule from quantum mechanics. using that experimental setup, we published a lot of papers on fundamental quantum mechanics and quantum information. And then we started to move slowly to a new experimental setup because this setup, the first one, does not allow us to, let's say, propagate or transmit photons. So we went to multi-core fiber optics. This is a single cladding which have many cores inside, and you can propagate light on each one of these cores. Many papers have been published on the subject from the group. And at some point, using what we have learned at the laboratory, Gustavo Lima and Stephen Walborn, which are two members of this research line, discovered that they could apply our understanding of these multi-core wave fibers to produce self-testing quantum random number generators. And in this way, they created a startup company called Secure, Secure in collaboration with a Polish researcher, Marcin Pawlowski. Probably some of you know him. He's working on quantum information too, randomness and other topics. They have secured funding for $300,000, and they have already sold about $50,000. Their company is right now undergoing the Valley of Death, which was mentioned by Paulo Nussenzweig in his talk. So they are looking for funding. It seems to be that last week they were more or less successful in convincing some funding agency in the country, private agency, to give them some money. And I'm doing also some movements to get some money too from telecom Chilean companies. So maybe this company will survive the death of Bali, and they will make money. And in the meantime, we have been extending our capabilities to work on multi-core optical fibers and installed a network based on these fibers across our campus. So we have physics department at the Faculty for Science and Mathematics and installed a fiber, multi-core fiber, which go from our faculty to the engineering faculty. So this makes more or less 1 kilometer in length in both ways. So we have 2 kilometers. And we have several fibers inside the communication network. We will use this to do two things. The first is that we want to perform quantum key distribution using higher dimensional quantum states, let's say Q-quartz or something like that. So quantum cryptography in a real-world setup in higher dimensions. The other idea is that we want to study classical communication protocols, but using multi-core fibers. Why? Because there is right now a huge problem with the communication network, and that's the big crunch. The bandwidth is not the one we want. So we have to increase the bandwidth, and one way is to use these multi-core fibers. And the last research line is novel light sources. This is at Universidad Santiago de Chile in Santiago. Two main researchers, Felipe Herrera and Dinesh Singh, they are working with what are called metal organic frameworks. These are crystals formed by metals with organic ligands. The chemistry of these compounds is wild. So there are more than 80,000 different possible MOFs. And what we are doing with this MOF is that we have discovered that it's possible to tune the MOFs to find the metal and the organic ligands in such a way that you can enhance the nonlinear properties of this crystal. In fact, we have been shown with experimental data that it's possible to produce second and third harmonic generation. But for that, we have to undergo a long process. And now we're able to grow the crystal to 6 millimeters size, more or less, in each axis. They are very transparent. They have not many impurities, and they produce second harmonic generation and third harmonic generations. And we hope that we can use this crystal to create pairs of entangled photons and triplets of entangled photons with a high ratio. What is the advantage of this stuff is that they are very cheap. Each one of these crystals is about $150. If you want to buy a comparable crystal in the market, it's about 5,000 euros. and you have to buy it in Lithuania or something like that. And we are also considering to start a company based on this result. Now, the productivity of the Institute in the past 4 years was of 137 papers, 94 of them in Q1 journals. So thank you very much for your attention.
Thank you, Aldo. People in the room, any questions? This time I have one that is concerned with the governability. Why you have chosen to be a non-profitable company? What are the advantages? How you manage not to go to prison, and etc.
Yeah, that's a good question. We are forced to be a non-profit corporation. If you want to get the money from our government, then that's the way to go. You have to be a non-profit corporation, okay? But that has been changing from government to government, okay? We had bad luck, and the government at that time forced us to become a non-profit corporation, because they say that if you are a corporation, then you are more or less independent of your university, which is never the case because the universities pays our salary, so you are never independent, okay? But that was the idea at the time, but I don't like it.
Okay, so this is part of the question. You could see no advantage
Yeah.
even in helping to write people or
there is no advantage at all. Let's
buy
say. It makes no difference. No,
for
it
nothing
makes no
like
difference.
this, it was
No.
a good plan.
Yeah.
Important.
Yeah, because I belong to a private university, so if you want to buy something, it's very fast. It's not a state, a university of the state.
Okay. Any more questions? So,
Hi there, this is Thiago Alegre from University of Campinas. So you mentioned about the budget, around like $10 million.
1 million
1
yearly.
million, 1 million a year.
Yeah.
And you mentioned that this is spread among all your groups.
Yeah.
But is this only to foment or to implement the interaction between groups, or also to fund all the research and buy the stuff, etc.?
We pay everything with that money except our salaries, which are paid by the universities. Let's say we pay the scholarships for undergraduate and graduate students. We pay the postdoctoral fellows. We pay the equipment we buy. We pay travel expenses. We pay the administration, taxes, because we have to pay taxes too. So everything comes from this $1 million every year. So it's not that much money, let's say. That shows you a big difference in the scale, because here when Paulo was speaking to you and Melita Coiler was speaking to you, they speak about hundreds of scientists doing quantum physics, and the quantities also were very large, the money. We don't have that luxury in our country. We have few guys, let's say, if you ask how much people is working in quantum physics in Chile, it's about 10 people. That's it. And the funding is very limited. So we have to choose very wisely what we are doing.
okay, so let's thank again Aldo. So now we will have a talk from Juan Pablo Paz that I will need to manage from here also. So Juan Pablo Paz will talk to us, and his introduction is already made in the slide. So,
Interinstitucional de apoyo.
Sorry.
Okay, thank you for the opportunity of being here. I'm going to talk about the Argentinian Quantum Initiative. The official name is not Quantum Initiative, it's the Programa Interinstitucional de Apoyo de Fortalecimiento de Ciencia y Tecnología Cuántica. That's in Spanish. And the story of this Quantum Initiative, let me call it that way, is similar but not completely identical to the one described by Paulo earlier. It started, the ministry approved the Quantum Initiative, the creation of this program in June last year, 2022. And then in July last year, a committee was appointed by the ministry of 12 experts, scientists from Argentina, coordinated by Marcos Saraceno. The names are there. I'm not going to read them all. The only thing I want to mention is that there are some people that were appointed as experts from the ministry, and then there are 4 people that are acting representing institutions. One is the Nuclear Energy Commission, then the other one is the industry and the Institute for Technology in Industry in Argentina. The other one is the Institute for Science and Technology of the Defense Department. And then the other one is the CONICET, which is the National Council for Research for Science and Technology. These 4 institutions participate of the program formally, and that's important for us because there is some commitment from them to participate. So the creation was in June, the appointment of the committee was in July. We requested that the committee present us with a document, with a survey of the situation internationally, nationally, and with some recommendations of what to do to promote quantum science and technology in Argentina. This was in July, as I mentioned. The committee presented the document in October, and then the ministry, based on the recommendations, there was some discussion, and 2 actions were approved in December, 2 specific programs with some funding allocation, and they are active now in March 2023, and they are going to be resolved basically in the next few months. We are planning to allocate funds in August, and in the next few months also to make some other announcements of other actions. So the program for this talk is, first I want to briefly discuss the content of the document presented us with by the experts, and then I will review what are the actions made by the ministry, taken by the ministry. I wanted to also mention that I am myself a quantum scientist. I guess that some of you may recognize me as in such a sense, but I'm speaking here as Secretary of the Ministry for Science and Technology of Argentina. So I'm not here as a scientist, but as the Secretary of the Ministry, telling you what the Ministry is doing. Okay, so the content of the document and the survey, what is the situation of quantum science and technology, quantum science and technology related to second quantum revolution in Argentina. So the finding of the committee is not surprising. We knew it. There is a small but thriving community in Argentina, which has some international recognition, and some high quality research is being produced. So far, and this is different from what was happening in Brazil, in Argentina there were not previous actions taken by previous governments related to funding specifically quantum science and technology. So there are experimental and theoretical efforts existing in Argentina. In the experimental side, the documented analysis, there are about 15 active laboratories, approximately 30 senior researchers and 30 PhD students, and in the theoretical front, a bit more, 50 senior people and 50 PhD students approximately. They are concentrated in the experimental ones in like big centers, universities such as the University of Buenos Aires and Cordoba, and the Nuclear Energy Commission in Bariloche in particular, and also at in the INTI, the National Science and Technology for Industry, basically metrology, and in the Defense Department in quantum communications. And the theoretical research is spread to other smaller centers in other areas. La Plata, in particular, is strong, and there are other provinces in Argentina where small university or research institutes exist where quantum information research is being done in the theoretical sense. What is being done in the experimental groups, just to mention a few topics, there is quantum optics in several places. In Buenos Aires, there is quantum information, cold atoms and cold ions experimentally. There is quantum metrology in the National Center for Technology for Industry, quantum metrology in the electronic and optical domains. And there is quantum communications and quantum optics in the Science and Technology Institute for the Defense Department. There is in the Nuclear Energy Commission, especially in Bariloche, there is superconducting circuits being produced and studied and used. Also quantum optics, materials and sensors, and different topics of research. NMR, also in Bariloche, and in Cordoba. NMR in Cordoba is very strong. Quantum optics as well in Cordoba exists. And these are the areas that are covered in Argentina related to quantum science and technology's second revolution. The committee also presented some recommendations, which I'm going to skip, and basically focus on what is being done by the ministry now. So in December last year, so a couple of months ago, we approved here at the ministry 2 actions, which with some specific allocations of funding, which are approximately the equivalent of $5 million US dollars in 2 actions. These are pretty obvious actions. They are among the ones with variations that were proposed by the committee, but we discussed and we thought of what was the best way of doing this. Action number 1 is aimed at recruiting new people. So if you are a young scientist that has experience working in quantum information and quantum science and technology in general, in high quality research groups abroad, and want to settle in Argentina, there is an opportunity, and we have funding available for creating new laboratories of up to $1.2 million US dollars, basically directed at buying, purchasing equipment and supplies to build a new lab. These maximal amounts can be discussed with justification. There will be an evaluation by an international committee that is being appointed right now and will be announced in the next couple of weeks. I will tell you a bit more about the timing of the different steps of this process. So, but the action number 1 is creating new laboratories directed by young researchers. There is a link in there where you can download all the relevant documentation and the application forms. There is a white paper that you have to submit. It's not complicated. And the white paper is going to be evaluated by the international committee, and there will be invitations to submit full proposals. The action number 2 is also quite obvious, strengthening and promoting the activities of already existing laboratories in Argentina that are producing high quality research in quantum science and technology. Here, the level of funding is lower. It's the equivalent of $500,000 US for purchasing medium-sized equipment of replacements and so on. This is also open, the call. There is going to be, as I mentioned, an international committee that will make recommendations, and based on these recommendations, the ministry will decide will allocate the funding in August. So we are planning to end this call, the process of related to these 2 calls, in August. The call number 1, the one aimed at promoting the settlement of new laboratories here in Argentina, is going to remain open, and decisions will be taken as soon as proposals are received. But we hope to choose the first set of proposals that are approved in August. Finally, there will be more announcements made in the next couple of months. One is going to be related to larger programs focused on specific areas of quantum science and technology. The 3 areas that are going to be chosen, also the obvious: quantum communications, quantum information processing and simulations, and quantum metrology and sensing. Probably we will have we will promote the activities, joint activities of different groups aimed at specific projects in these areas. And the other area is education and outreach. We are going to have news in the next couple of months. And with this, I think that I'm done, and I leave time for questions. Thank you.
Thank you, Juan Pablo. Any questions? So we see that we need to include Argentina in the QRECA map, and there are some millions of dollars appearing. Everyone is satisfied? Are you 100% sure? Okay. So thank you, Juan Pablo.
Thank you, Marcelo.
Again.
Ciao, ciao.
Ciao. And our next speaker, also from elsewhere, we'll have Rafael Chaves, who can start sharing screen, please. And Rafael is a researcher at the International Institute of Physics, and it's now time for us to focus a little bit more on science than on the plans for making technologies. So,
Marcelo, can you hear me and see my screen?
Yes, we see your screen, and everyone here who was quite sleeping, now they will make questions for you in the end. Thank you.
Okay, great. Yeah, so let me just open my clock here that I don't pass the time. So let me start thanking you for the invitation. It's my first time in the March meeting, so yeah, thanks. I will talk about like one line of research that we follow here in our group in the International Institute of Physics in Natal. So it has to do with quantum networks. Okay, so the first thing to say is what is a quantum network. So it's just like a classical network that we are using, like the internet with so we have nodes and we have links interconnecting these nodes. The difference now in a quantum network, at least from our perspectives, that instead of like having classical channels over which we send classical bits, we now have quantum channels, for which we can send like superpositions, qubits, entanglement, and so on. And so this is the essential feature, like these quantum links, they can be connecting classical devices just as our usual computers, or they can be interconnecting quantum devices. Like you could think of like a node having the IBM quantum computer or whatever like this. Okay, so that's the basic idea. And let's see where we are now. So like making a short review over the last 10 years. So in 2012, we had this breakthrough, like the quantum teleportation. So like establishment of entanglement, like over 100 kilometers in free space, like in the Atlantic. 2016, we had quantum teleportation again, a smaller distance. But what is nice in this experiment here is that we are talking about a metropolitan fiber network. So like basically showing that an infrastructure that was built thinking of classical communication can also be used for quantum tasks. So 2017, we have like the real breakthrough in this field. That was the launch of this satellite, the MISSIUS satellite. That is so it has like embarked a source of entanglement, and it can generate these entangled photons and communicate them, like share them among very large distances on Earth, like surpassing 1,000 kilometers, as you can see here. In this first experiment, like they violated the Bell inequality, so like unambiguous proof that actually the particles that they were sharing between these two very distant points, like over 1,000 kilometers, they were really entangled. So they used the same setup, like slightly different issues here, but to establish a quantum key between two very intercontinental points, and they did like the first quantum sky in history. Like basically, they used this key that was generated to communicate securely. So 2021, this I find like another breakthrough. Is the first medium-sized quantum network, again in China, where they used like the MISSIUS satellite and also fibers on Earth to establish like over 150 nodes quantum network covering distances over 4,000 kilometers, and establishing like secure nodes among universities, banks, military stations. So this is another one from 2021, again in China. I mean, the distance is very small, 1 kilometer, but the idea I find very neat, that you use drones to like surpass geological defects. So like you have a mountain between two stations that want to establish a quantum key. So you basically can use drones to share entanglement between these two nodes. So, I mean, it's not sci-fi anymore. It's not something that we theoreticians, I'm a theoretician, are thinking. It's like something that people are actually building. But for what they are building that? And there are many reasons. Of course, the first one, or like the most paradigmatic one, is quantum cryptography. So the idea here is that we have Alice and Bob, a sender and a receiver that want to communicate securely. And to do that, like the only known way to do this, that it's really secure, is to use a secret key. So Alice has a secret key, Bob has the same secret key. This key is really secret for everyone else. So they can use this to encrypt and decrypt in such a way that if we have a hacker, eavesdropper here in the middle, because he doesn't know the secret key, he's not going to get any information about the message that is being sent. The problem, of course, is how we establish this key if the two persons are far apart. And classically, there is no way of doing that. But with quantum physics, we can do it. So historically, the first one to notice this was Bennett and Brassard in '84. They realized it, so it's actually a quite nice story, but like they realized that using the no cloning theorem, they actually could come up with a very simple protocol that we call a prepare and measure. So basically, Alice, she's going to prepare a quantum state that will encode like the basis and also the message that she wants to send. And Bob, on the other side, he has a measurement device. He will measure this quantum system. And by following a very simple protocol that doesn't matter here, they can establish a key. Secret key that they can use to communicate securely later on. The problem is that unless experimentally we really follow like very closely the theoretical protocol, this system here is open to attacks. And actually like there were quantum attacks on this system, so like quantum hackers that were able to exploit failures in the experimental implementation and crack this kind of system here. But then we can move to something that it's like the ultimate level of security, and it's based on the violation of a variant inequality. So the basic idea here is that by violating a variant inequality, only looking at the data that we generate in the experiment without knowing anything about the devices we are using, we can guarantee the security. So it's what we call a device-independent quantum information processing. There are many things beyond crypto. So like we can think of quantum teleportation is this idea that we can use a shared pair of entangled particles plus classical communication to send quantum communication. So we don't need to actually send quantum systems and just pre-share entanglement and use our phones, and we are able to send the information that it's contained in quantum systems, or like the reverse, that it's the super dense coding, where we use entanglement plus quantum information to send classical information more efficiently. We can think of entanglement swapping, that it's basically like teleportation of entanglement. So it's this idea that if I want to establish entanglement with São Paulo, I mean Natal right now, so it's very far. The chance that the photon that I generate here arrives there, it's very small. But instead of doing that, I put a lot of intermediate stations here, like it's what we call a quantum repeater. And by doing this teleportation of entanglement, I guarantee that in the end, I'm going to have a particle that it's entangled with another particle there in São Paulo. Or more generally, I can think of like many different scenarios in what's called the distributed computing, where the basic idea is that using entanglement that it's shared in this network, I can use less bits, I communicate less bits to achieve a certain task. Okay, so this is the big picture. So let me talk a little bit now about what we do here. So first, the theory part. And one thing we do is like, how can we certify that the network is really quantum? So, I mean, I don't have access to all the parts of my network. Some devices I bought from a third party, I'm not really sure I can trust them. So there are ways of like certifying that the network is really quantum. It's working as it should, only looking at the data. So this is again, this device-independent framework. And the basic idea here is that the classical model defines like a set, could be a non-convex set like this flower you see here, what is generated in my quantum experiment. It's a point, and basically what I want is to check if this point, if this data that was generated in my experiment falls inside or outside the set. If it falls outside, I'm proving in the stronger possible manner that my data is actually quantum. It doesn't have a classical explanation. So this looks very simple, but it's horribly complicated. But by now we have not only our group, but many other groups have developed a lot of tools to analyze this problem. And we try to always work in collaboration, close collaboration with experimentalists that make proof of principle experiments, or even like actually implement these networks to do useful things. Like, for example, in quantum metrology or in this distributed computing. So just to give like two concrete examples, this work from last year with the group of Fabio in Rome, where we did a very simple network like Alice, Bob, and Charlie, and we used that to do like entanglement swapping in a device-independent fashion. And what's nice here is that this network actually involved like 2 different labs that were in different buildings inside the Sapienza in Rome. And the nice thing is also that we integrated many different technologies. So like we have a free space link, a fiber link, like a SPD, a C source, a quantum dot source. So like really showing that it's possible to integrate different technologies to grow these quantum networks. This other experiment, it's very recent. It's from this year, where we did another kind of network. It's called the triangle network. And the basic idea why we did that is that this network allows us to test non-classicality, to allow us to test the non-classicality of a network without the need of freedom of choice. Like every observer here, Alice, Bob, and Charlie, they are always measuring the same observable. And this is something that it's not possible in the usual Bell's theorem. Okay, so to finish, one other line that we are following since some years here, it's like understanding the properties of the future quantum internet, of these quantum networks that are being built now. And basically what we want to know is how can we make these networks more efficient to communicate on information. And one of the key properties of the actual internet is the fact that it's a small world network. So we have hubs in the, so this is it's an actual photo of the internet. And you see that we have hubs here that make this network small world, meaning that this network is much more feasible to communicate information. And okay, so without entering in any details, like using network science, we could prove that like fiber networks, they are very inefficient, but they can be made efficient if we employ these quantum satellites, these satellites that can share entanglement over very large distances. So this is cool because like it shows us how we can develop the future quantum networks and future quantum internet. Okay, so here's just, I'm sure I spoke very fast. I'm sorry for that, but the time's short. And here is just like a summary of everything I said. So I finish here and hopefully we still have time for 1 or 2 questions. So thank you.
Thank you, Rafael. And yes, it has to be fast. This is the time we have. So, wants to make questions? They are shy yet, so I will make mine. And when you say that the use of satellites will be essential, it's really to make the hubs, but you complement it's only including satellites in the fiber network, I think so, or not?
Yes, so because of the properties of fibers, you cannot really like surpass over 100 kilometers. It's like more or less the limit of how far you can send photons without like having a rate that it's really slow, because you always have to consider the rate that you want, right? And so basically like a fiber network would be very disconnected and it doesn't have this small world property. So like meaning that if you want to connect 2 nodes, you need to make like a lot of entanglement swaps. And every entanglement swap you do, you decrease the quality of your entanglement. But by allowing this quantum satellite, you generate these hubs. So like the size of these balls here, they show the connectivity of the node in the network. And by using quantum satellites, like you generate these hubs, and these hubs, they act as atalho. I forgot the shortcut word in English.
Shortcut.
As a shortcut between any 2 nodes in the network, so we can recover this small world property and make the network very efficient to do quantum communication. So like basically to interconnect any 2 other nodes in the network. Yes. So satellites are going to be needed. That's the conclusion.
So now we have 2 raised hands, one in each extreme, so I do not have a satellite.
I'm Bárbara Amaral from the University of São Paulo, and I saw that you had a lot of collaborations with experimentalists into implementing these works of quantum networks. But I didn't see if there, I couldn't read all of them. I wanted to ask if there's any perspective of having such a thing in Brazil.
Oi, Bárbara. Bom, well, this is a great question. And yes, so I mean, there are two reasons to look for partners outside. It's one is because these experiments, they cost a lot of money. Like, for example, for one of these experiments, we had to buy new detectors and like a lot of optical fibers. So, I mean, it's something that they have the money and also the time, because like, if you want to ask for something here in Brazil, you need to have the money, but you also have to wait like a long time. Maybe it's in the Receita Federal for months. I mean, who knows when the things will arrive. And these experiments, like there are many people doing them. So it's a bit like a run. You don't want to be stupid. So you also like look for partners that you think can do that in fast time. So I think there are many issues here. But of course, it would be great if we could do these experiments also in Brazil. But I'm sure that like we have the capability for that, like in Rio, São Paulo, Recife, even in Goiás. So it's just a matter of having the resources, I think, because the knowledge and the human capability, certainly we do have. It's just a matter of having more resources. That's a great question, yeah.
Hi, Rafael, it's Marcelo here. Can I just make a short comment that there is
yeah, sure.
There is an initiative now in Rio, and that is probably going to be expanded to other states to establish like the first test bed for quantum communication, experimental quantum communication connection network between institutions, and it's financed by the institute, the National Institute for Science and Technology and Quantum Information. So there is hope.
There is hope, yes. They will have a meeting in May, I think. I will be there, so I'm looking forward to discuss with all of you. Thank you, Marcelo.
Hi, Rafael. This is Thiago Alegre from the University of Campinas. Just one quick question about, so you mentioned about the protocols and the network, etc. What is the role of quantum memory in your, as you see your quantum network?
It's highly important, and I must say that like when we, like for example, in these papers here where we model the quantum internet, we assume to have perfect memories. Of course, this is a toy model, and in the future, we should be able to include the effect of memories. So in these models here, they are very important, but we don't use them. And for the actual experiments, they are not important for us because we generate and measure the photons. We are not really trying to store or retrieve any information. So it's like a prepare and measure scenario. We are generating the photons and measuring them as they arrive. So for this sort of experiments here, memories are not important, but for the future quantum internet, for sure, they will be very important.
So let us thank again, Rafael.
Thank you, everyone.
We are more than one talk later, so let us try to put things fast. And we'll have the pleasure now to receive a former member of IEP group, and nowadays a professor at the University of São Paulo. And Bárbara Amaral will talk to us a little bit about quantum bit commitment.
Thank you again for the opportunity to be here today. And different from Rafael, who just showed us a lot of published papers and finished projects, I'm going to talk about something that I haven't been, that I want to do, but I have no paper to show you. It's just hopes that we will have something very, very nice in a few months. So first, let's understand what is bit commitment. So this cryptographic primitive that we want to study. So to understand what bit commitment is, we can think about a simple example. And we have two parties, Alice and Bob, and they want to resolve some dispute. They are far apart from each other, so they kind of want to play head and tails, but they are far apart. So the problem here is, how do you play head and tails, how you toss a coin over the telephone? So there's one way of doing this. So Alice can choose head or tails and write her choice in a piece of paper and lock it in a safe. She sends the safe to Bob and keeps the key. Bob will toss the coin and will send the result of the coin toss to Alice. Now, with the result of the coin toss in her hands, she will send the key to Bob, which will now see what was Alice's choice, if she chose heads or tails. So if Bob will now open the safe, and if the result coincides with Alice's choices, he loses. And if the result does not coincide with what's inside the safe, he will win this dispute. But there's no secure way of doing this, although this is very important for many, many practical purposes. And why there is no secure way of doing this? Because first, Bob could use some brute force method to open the safe before tossing the coin. So he could just look into Alice's choice and just say that the coin toss gave the opposite result. Or another thing that could happen, Alice could send a magic safe to Bob, and she could change what was inside her magic safe after receiving the result of the coin toss. So she could just change so the result would favor her. So this is essentially bit commitment, but to make things a little bit more formal, everything starts with the commitment phase. So Alice commits to a bit B and sends a proof of her commitment to Bob, the safe. The waiting phase, in which nothing happens. And the opening phase, it starts if and when Alice decides to reveal her commitment, which corresponds to her sending the key to Bob. And this is going to allow Bob to check the authenticity of Alice's commitment. So for this to be secure, we need two things. We need commitment. Alice should not be able to lie about what the bit she chose, so she could not have a magic safe. And we need concealment. So Bob should not be able to open the safe, to guess the value of B before the opening phase. So Bob could not use brute force to open the safe. So we need to guarantee these two things, and this is basically impossible. So we can have one or the other. So there are many applications for that. So this is a primitive protocol in cryptography in general, from which many, many other important protocols are derived. So although this is impossible, this is important and it's implemented anyway. So we have not perfectly secure bit commitment protocols being implemented every day, but they are sufficiently secure for our applications. But if we can get something more secure in some sense, or perfectly secure, that would be really a great thing. Okay, so quantum bit commitment is doing this thing, and the proof of Alice's commitment is quantum information. Okay, so it's encoded in quantum information. So Alice's proof of her commitment is a quantum system which is in a state Ho0 if she chose the bit 0, or it's in a state Ho1 if she chose bit 1. there are results telling that this is also impossible with quantum systems. So it was already known that it was impossible with classical systems. There was some hope that this would be possible with quantum systems, but then appeared these two papers in 1997 in the same issue of volume of PRL, saying that this was impossible. Of course, I'm not going to the details here, but the idea is that security against Bob concealment implies that these two states have to be very close to each other. And on the other hand, if this is the case, if this is true, then the protocol can be mimicked using two entangled states, psi0 and psi1, that can be transformed into one another only on Alice's side, okay? So if the protocol is secure on Bob's side, which implies this property here, it is not secure on Alice's side because she can basically use what is known as quantum steering to cheat. Okay, so the proof is basically to showing that if the protocol is concealing, it cannot be binding, there cannot be commitment on Bob's side. But I like this phrase here. So our goal is first to understand what are these proofs, these no-go theorems, and see if maybe we can do something different. A lot of people had already claimed to do that, and they failed. It was not true. Someone found a way to include this in the no-go theorems in the end. Perhaps we're just going to be one more in the list of failed attempts, but we don't care. We're going to try anyway. And our idea is to restrict Bob's measurements in order to guarantee security on Bob's side, even if Ho0 is different from Ho1. So this guarantees that it could be perhaps secure on both sides. So what we are working now is to find ways to guarantee that this is possible. We have some ideas. We don't know if they will work, but we are having a lot of fun seeing if this is possible. And for those of you who know me, you know that I work with contextuality and quantum non-locality. And Paulo was hoping that I would say something about it. And this is mainly inside here in the ways that we are going to guarantee that Bob is doing what he was supposed to do. I'm not going to the details, but there is contextuality and non-locality inside my talk. It's just not going to explain you why. So our goals, first, understanding the assumptions in Myers and Lowenthal results, the no-go theorem results. This is already teaching us a lot of new things. I'm very happy to be working on these things. And of course, it would be the perfect case if we could find a way to evade these theorems and find a secure quantum bit commitment protocol. We would be famous if we accomplish that. But even if we don't get perfect things, at least we hope to have like less insecure quantum bit commitment protocol, because it is important anyway, even if it's not perfectly secure, or at least differently insecure from the classical ones, because maybe this is better from some applications. And we hope in the future to have both theoretical development, which is ongoing, and experimental implementations. So the team that has been working with this, first, the one who started all this talk was Charles Stresser, which is now at INPA in Rio. He approached Professor Paulo, who is here, to talk about it. And I was just arriving at USP at the time, so I was very lucky to be involved in this conversation. And now we have a project, a finance project by Serra Pilheira. And working on this, I have now Roberto Baldijão, is a researcher at our group, Júlio Camilo, a PhD student, and Letícia Lima, undergrad student. Okay, so this is our group at the University of São Paulo. We will be happy to have you visiting if you want. And I thank you all for your attention.
So, Barbara, I have one question. When you say restrict what Bob can do, so does it mean limiting the tools that he has to brute force open the safe, or does it mean letting Alice know which tools he is using, so that if he brute forces, she knows what he's done?
That's the second option. So if he tries to use brute force, she will know, more or less in the same spirit of BB84. So if our idea that we don't know if it's going to prove safe in the end, is to use something based on the Bell inequality or something like that, or contextuality inequality. So if Bob does not act as he should, as in the correct protocol, there is some violation of some Bell inequality that is not going to happen anymore. And Alice will only know that violation. So we have to be very careful, because if Bob tells a lot, then it's not going to be secure against Alice. So now we are just figuring out if these ideas are going to match.
I would just like to add that usually there's a saying in the United States that it's not that you can't break the law. You can't break the law and get caught.
Exactly.
And so here, the point is, we're not going to avoid Alice or Bob cheating. We're just going to make sure that they get caught.
Exactly, exactly. That's the idea. So just to add a few things. So I've been out of work for the past 5 months, so I have no idea what these guys have been doing. Probably they already figured it out. And I'm back to work in 3 weeks, and then I will learn if they have something to show me.
But we can catch one here. And
Yeah.
So thank you, Barbara. And let us move to our final speaker. It is Thiago Alegre from Unicamp. The first week when she come back from maternity leave.
Okay. So thank you everyone for enduring and staying until the last talk. I hope that I'll do in time. And especially because now we have like very great talk from Barbara and Rafael that already like introduced most of the things that I'll talk about it. So the idea here is more or less this. So I'll talk a little bit about how we did a quantum teleportation using optomechanics and what are the goals or the scene that we see for the future for this. Okay? So just one thing about a light-sound interaction. This has been an ongoing thing for a while already, either on waveguides or on cavities. So the idea is here that actually you couple mechanical degrees of freedom with optical degree of freedom on some of this device here. And this talk I will focus only on the cavity side. So I will look for an optical cavity and see what happened when you couple it with a mechanical motion. Okay. And this has two phases for the optomechanics, which is called the dispersive and dissipative. We learned from Lucas this morning about the dispersive, so I'll talk about both of them. And the main idea is this, for the dispersive, once you have some object that's moving and perturb your cavity, you end up like changing the frequency of your cavity. This is the dispersive side. So you basically just change like the mean refracted index here, so change the path length, and therefore you change the wavelength. And on the dissipative, you can also think about the same thing. So once you have an object that's moving back and forth, it can actually change the intrinsic or the extrinsic loss and changing, therefore, the overall rate of loss that your cavity sees. And on the dispersive side, we have seen like lots of things throughout the last like 2 decades. And we have like a device that has like a kilogram to femtogram size. And maybe the most famous one is LIGO, which then detected the gravitational wave using this idea of changing the frequency when there's a perturbation there. What I want you to focus in is that we can basically have like a interaction Hamiltonian that couples light, which is this A dagger A here, with mechanical motion, which is this X, which is B dagger B. And what is important here is that actually we can tune whatever the interaction we want. So depending on where we put the laser, we can have like a beam splitting Hamiltonian or a squeeze type Hamiltonian to read and write the mechanical motion. And that's what we did using the quantum teleportation here. This was done, led by Professor Simon Globacher. And one of my students was there in a superposition between here and there. And the main idea was already explained by Rafael and show like the great idea of quantum teleportation. And I just highlight some of the main topics here for the quantum teleport. And I have just a little cartoon here showing how we do that using entangled photons with phonons. So the idea is that you have like an entangled pair, and you give a little bit of it to Alice and to Bob. And Alice will then mix this entangled state with an unknown state that she wants to teleport to Bob, so a psi state. And then Alice does a conditional measurement or a Bell measurement over her entangled state mixed with the psi state. Knowing the information, she then sends a classical information to Bob, tells him whatever she noticed about that, and finally Bob does a unitary transformation to recover the psi state. And of course, this is, as we learn like from the last like 5 topics, this is very fundamental for quantum information and quantum information processing. And what we did is the same, but now looking into an entangled state between a mechanical motion and a optical degree of freedom. In this case, the polarization of a photon, a vertical or horizontal polarization. And to do that, we use the so-called optomechanical device, where we have an optical mode coupled to a mechanical motion, in this case, that vibrates at 4 gigahertz. And that's important because you can then have an optical cavity that can tune whatever is your interaction Hamiltonian once you shine the laser on the blue or on the red side. And to start the process, we actually fabricate a couple of this device because we need to have 2 exactly equal devices, so homozygote twins. And in fact, what is done is really a little bit of brute force. So you fabricate like hundreds of devices, and you measure all of them until you find two that are exactly the same frequency, optical frequency, and also mechanical frequency, okay? So then you have these two of them, and you can then start your protocol. So you put both of them in a dilution fridge, and this is important because then your mechanical motion, it is on the ground state. So you don't need to initiate, it is already on the ground state for the mechanical motion, since it's, the mechanical motion is of 5 gigahertz mechanical motion, so it'll be in the ground state to around like 100 millikelvin. So then you start by shining a light on the blue side, so you write your state, so you create a phonon or on Alice or on Bob. So you entangle this state, this mechanical motion state with the light, and the idea here is actually you basically decide. You just tell like the Alice is the vertical, Bob is the horizontal, and then you mix polarization again. And after that, what you do is you mix Alice's path with your side state and do a Bell detection measurement. And this is a conditional measurement, so depending whether you get the clicks, so on the top 2 detectors or lower 2 detectors, you get like one of the states, so you know already what is the teleported state, if it is with the plus sign, or on the opposite, if it is on a cross detector there for V1 and H2 or H2 and V1, then you have the other phase. So, but knowing this table, you can then decide which is the unknown state that you want to teleport. Then you tell Bob, which is the other device that is in the dilution fridge. And you need then to test if the system or the state was actually teleported. And that's where comes like the idea of the long lifetime to the mechanics. Since this is not in the optical domain, it has a very long lifetime. So this device can have like up to 2 millisecond lifetime, which is a lot when you compare to the optics domain. So then what you do is you recover whatever is left on the entangled state here. So you do another pulse, a red pulse, to read what was stored in the device. And at the end, you basically measure your device, because our unitary state here was actually just measured because we knew what was the system or the state that we want to teleport. And then we tested if the fidelity was above the classical limit, which is the 2/3. And we did that for all the polarization, even like the diagonal and circular polarization. And all of them show that you are above the classical limit. And that's important because we show that this is really a quantum teleportation, but it took 35 consecutive days to measure. And when I say consecutive, it's really consecutive. Like the experiment was not shut down for 35 days. And this is mainly because we are limited by heating. Any scatter light that was inside the fridge could heat up the system and take out your mechanical motion from the ground state. So that comes the second part that I think I'll have time. So Marcelo will stop me at some time, which is the idea of dissipative automechanics. So again, as I mentioned, dissipative is when you modulate the losses of your cavity. And in this case, maybe you can modulate the intrinsic loss or the extrinsic loss, which means you can couple more or less to the external world. Okay, this has been done in the past, but and has like some advantage compared to the dispersive case. So here in the top is the dispersive case, which is it's good when you have the dispersive because you are scattering light from the cavity to the cavity, so it's doubly resonance. It also couples the number of photons inside the cavity, but that's also a problem because since you are using scatter light from the cavity to the cavity, any unwanted absorption will lead to a extremely large heating. In the case of the CPRIF case, you can actually scatter photons from the waveguide to the cavity. So only the photons that are already in the process of coupling to the mechanical motion, it will be already in the cavity. So basically your cavity is empty and you only scatter photons when you do the interaction. So you have like lower number of photons in the cavity, which might help with the heating or the extra heating. But again, like has been shown only with low mechanical frequencies and actually with a very low coupling rate. And I hope that I showed you that we could overcome that. So this is our setup. And again, like this was fabricated by Rodrigo in his superposition state. And these are two coupled cavities, optical cavities, that are coupled to a bus waveguide here. And the main idea is that when you have like two optical cavities and you bring them close together, you can actually have a splitting between the two states, like a anti-crossing for the two optical modes. And also what is important here is that you saw that we start with two cavities, one that is coupled to the waveguide and the other one that is not. So the loss is also symmetrized. Not only the frequency is splitting, but the loss is also symmetrized. And this is important because now if we have an object that changes the optical frequency, that also brings you back and forth here in your coupling position, which then causes the total loss to change dramatically. So, and that's the important part, that if you have a system which has a very large dispersive coupling, it will have a very large dissipative coupling, because you are coupling one to the other. And that's what we did for the, Marcel is waking up here. So that's what we did. We are near time, okay. Cindy is saying that we are near time. So that's what we did for the setup here. Let me just like go very quickly because I want to show you the results. We do have the two optical and two mechanical modes. And what is important here is this slide here. So we did measure the mechanical motion when we tuned the laser. And we could see the two mechanical modes because we have two objects, but since they are far apart in frequency, we can distinguish one from the other. But more importantly, when you see what happened to the transduction at a given frequency, for example, the mechanical frequency for the first device, you clearly see that this transduction is asymmetric. And this is not explained by the dispersive optomechanical. And that's the key important here. This is only explained if you have dissipative and dispersive together. And it's just a last cartoon here. If you look for the dispersive or dissipative, they are out of phase. So you can have like at frequency 0, one there's no transmission, or there's no change in the transmission, and the other one has. And of course, depending on where you are, you can have like destructive or constructive interference between the dispersive and dissipative interaction. And that's the reason why you see the so large discrepancy between the dispersive and the dissipative. So, okay, so to finish here, we just show that we did measure a very large dissipative coupling in a very large frequency, so 5 gigahertz and about 3 kilohertz, and this is 100 times larger in frequency than any other device, and 10 times larger in any other coupling. So we believe that this shows the way that where we can use the dissipative coupling to devices like the other one that I showed for the quantum communication, and then have less heating and therefore faster communication. Okay. Okay, so I will thank you, everyone, and thank you, Marcelo, and thank you, everyone, to stay and for so long time. Thank you so much.
Alan will be the one to have the question to Thiago.
Hi, I'm Alan from Unicamp. When you showed the fidelity chart, I think in the beginning, you showed that depending on the polarization, you had kind of different results. So you had like vertical and horizontal polarizations kind of better than the other two ones. Do you have a hypothesis on that?
This is a little bit, so to measure the polarization, actually to rotate the polarization, we use apocal cells. So that's, and so there was a little bit of a loss on the apocal cells. So for the vertical and horizontal was much easier to measure because it was just a single state. But for the diagonal and for the circular polarized, you need to add a phase, which therefore imprinted enough a little bit noisier the signal at the end.
Whoever needs to understand what a poker cell is, ask Thiago after the
Okay, so
meeting.
poker cells is a device that rotates the polarization.
Great. So before we all thank Thiago and all the speakers again, let me thank the APS for sharing with us this possibility of being part of the March meeting remotely, and especially thank Nathan and all the SAFIR, ICTP, IFT to host us and to all the efforts that he has made to make it happen. And before the final applause, I would suggest that just after it, we have a picture here because this was the reason why Aldo is here. I said to him, you need to come here to be part of this photo. So without the photo, he can make me go to jail in Chile the next time I be there. So thank you, everyone, to all endurance.